Hey everybody, Casey Muratori here. I am just continuing down the list of suggestions I got on Twitter when I asked what videos should I post to try and help get the word out that our Kickstarter for Meow the Infinite is now live. This is a really cool graphic novel series that we do here at Molly Rocket that's all ages, and it's a really neat story, and the art is fantastic. Please check it out if you get a chance. The link is in the description. Anyway, one of the suggestions I got was to post the lecture I did at the University of Twente in the Netherlands. This was a lecture that I was invited to do during COVID, so it's actually just via video conference, which means I have a really good recording of it because it's what was streamed. You'll be seeing it exactly as they saw it when it was presented. The lecture is about optimization, and it's a case study in how to take something that was very slow before, it took like a minute to do or something like that, and how to get that down to basically instant. And, you can't always do that, but sometimes you can, and this is a case study of one of the times where that was possible. So I hope you enjoy it, and again, check out the link in the description below if you get a chance. Without further ado, here's my lecture from the University of Twente. Okay, so this is a kind of unusual lecture. I got asked to give it, and it wasn't quite enough time for me to do a lecture in the traditional style, which would be kind of like a 1-hour thing where everything is set up exactly right and it's all fine-tuned. And I said, well, I don't really have time for that, so I don't know if I can really do it. And they said, well, you can go ahead and take a 2-hour time block, because that's how we normally do things anyway, and if you want to do something informal, that's totally cool. So I was like, awesome. If I can do something informal and I can talk about whatever I want to, then we can do something probably pretty cool. It's just going to be more like a class kind of a thing than a traditional lecture where there's like slides for everything. And, so we're going to be drawing stuff out on the board and that sort of stuff. But, other than that, it should be pretty smooth sailing. So this is a stream directly to the University of Twente. I think I've pronounced that roughly correct for an English accent. I'm not sure. I asked, but my pronunciation is not great. And this is something that is a lecture that's sort of general audience, but to a technical, a more technical audience. So it's, it's not going to be the most technical lecture, but it's also not going to be completely non-technical. And what I wanted to talk about, because since I was allowed to talk about anything I wanted, what I wanted to talk about was a actual concrete example, a case study that kind of shows why I think software is slow, and I do think software today is very, very slow. I don't know how controversial of a statement that is, because, a lot of times if I say software is slow, maybe you get some pushback. But I feel like a lot of times now the pushback is not as strong. I think maybe people are coming around to the fact that software is a lot slower than it should be. And so, this lecture is kind of trying to take the next step, which is to say, well, if software is slow, why is it slow? And maybe what are the things that people are not taking into account? Excuse me. That people are not taking into account that, if we started to think about, we would actually be able to make software that was better, right? Because at the present moment, a lot of people, this is a lecture to university, a lot of people actually study for a while to become computer programmers. In theory, one of the things that computer programmers would learn to do is to write software that's very good, that has a high quality bar, that is performant on the machines that they are using. You would assume that some of these things would be true. And yet, even professionals in the field who've been working for quite some time, so not only have they had the education, but they've also had experience in the industry, you can take people who've been working for a very long time, and they are still not actually writing software that performs particularly well on the computers that they're using. And so this is kind of this is something we're going to have to fix, because at some point there's going to have to be some awareness of the fact that we're, at the very least, spending a ton of computer time doing effectively nothing. Like, we're burning a lot of power, we're burning a lot of money, especially when you think about paying for data centers and that sort of thing, on software being slow. And so it's just a question of how do we start to push people towards learning how not to make software so slow, how to make it faster by default, and what are the mindsets involved in doing that. So this case study is about the grass planting algorithm in the witness and the performance characteristics of that. And the reason I picked that was because it is something that was pretty slow, but it was written by people who know how to program relatively performance-oriented code, so it wasn't like a complete disaster. It wasn't written in like an interpreted language on top of, all these things where there was just tons and tons of stuff underneath it that I would have to piece through. It was written, in C++. It was written custom for that thing, for the most part, and so I can take it apart and show why it was slow, and of course I can also show the one that I rewrote on that project to be fast, and I can also show direct comparisons about how fast we're talking about when we're talking about fast. So before I dive into that, let me just try to motivate things a little bit here as I drop the pen. Let me try to motivate things a little bit here in terms of understanding why you might care if software is slow. So some people are still under the impression that doesn't matter if software is slow. Just let the software be slow and it's someone else's problem. Like, yeah, the user has to sit there and wait for this thing to do whatever it's doing, but that's okay because the important thing is getting the code done or something, right? Or that you don't have crashes or something, right? There's a mentality that says it doesn't matter if the code is slow, so we shouldn't care about the fact that it's slow. So I wanted to list just 3 brief things as an example of why you might care even if that's your attitude. So the first one I want to say is Windows CE, if you've ever heard of this, and a lot of you probably haven't, to iPhone. This to me is the #1 best, most obvious example of why performance matters. So Windows CE was actually the thing that you used to use on a handheld device. So prior to the iPhone coming out and Android, which of course was after iPhone, prior to that shift, Windows CE was actually a handheld operating system with a series of handheld devices. They were, I don't want to say widely used, but a lot of business users used them. And they effectively provided everything an iPhone provided and more. So, the original iPhone, when it first came out, had almost nothing on it. It had like a few little apps that Apple had written. There was no App Store when the iPhone originally launched. And it couldn't do a lot of things that Windows CE could do. Like Windows CE had little like Office app stuff on there and all these things that you could do on there. The difference between these two things was literally just the latency. Like it was literally just the fact that Windows CE, if you go back and look at these devices, they are slow, they're clunky, the touch is just kind of, you click on it and it's slow and it's very, very, it just feels horrible to use because everything you're doing, right, is very latent. The touchscreen was lousy, the lag was extremely large, and it wasn't really very animated. It was just a poor experience using the device. And going to iPhone, they literally just introduced something with a nice touchscreen that was like full frame rate. 60 frames a second or at least 30 frames a second on everything you did. When you dragged, it would follow you directly, right? This shift was so powerful that literally just introducing a low latency device with less features than another device completely changed the industry. That was it. Because now it was fun and interactive and it felt good to use your phone and it felt crappy to use this. When things feel good, people want to use them. And performance, specifically latency, the amount of time between when you try to do something and when you see the results, is critical for getting users excited and invested in something that you do. And this to me was the best example because if you look at an iPhone, you cannot tell me that it had more features than Windows CE. It didn't. It had less features, but people liked it better. And they liked it better because it felt better. Now, this continues to this day. What does an iPad Pro advertise? Well, have you ever seen their videos? They're like, artists, you will love this iPad Pro because our pen has a 30 millisecond response time. They literally say this a 30 millisecond response time, right? There's 1,000 milliseconds in a second. A 30 millisecond response time is around 30 frames per second, right? 16 milliseconds would be 60 frames a second. 30 milliseconds is around 30 frames a second. So this is basically advertising 30 frames a second on your drawing. And they say this is much better than everything else. You can see how responsive it is. They show video and slow motion video of how far behind the pen the actual stroke lags. This is advertising for Apple. And the only thing they're advertising is low latency. Okay. Number 2, and maybe I've gone on a bit too long, so maybe we'll just do 2. Maybe I'll skip the 3rd. Hopefully this sells it a bit. Everyone everyone understands this intuitively, but it's performance that is what's being sold here. One other one is Mapquest to Google Maps. This one's very interesting to me because not only is it the exact same kind of shift, Mapquest was like a static map and you clicked on it and it would like refresh. This was the mapping service most people used. Google Maps came out, you could drag the map around. It would page in real time. You could drag it around. You could zoom in and out, right? This is gone. This is now the predominant mapping program. They don't really do anything different. I mean, later, much later, Google Maps actually added some features, obviously that Mapquest didn't have, but by and large, when it came out, it couldn't do anything Mapquest couldn't do. It did the exact same things. It was just low latency. You can drag the map, you can zoom it in. That's engaging. It's fun. Low latency equals success in a lot of cases, even if you do less. And the reason that I put this up here, especially, is to note that Google Maps is still extremely slow. It's a very low performing piece of software, even back then, and definitely now. But because their competition was even slower, all they had to do was be slightly better. You know, if you can go to from something that's static to something that's 100 milliseconds or 500 milliseconds of latency, that's still a pretty big deal. So not only does getting it exactly right help, not only does getting to 30 frames a second or 60 frames a second matter, but getting from like a frame every couple seconds to several frames a second is also great. You don't even have to get all the way before you start being very competitive to people, because most people's software is extremely slow. So just being slightly less than extremely slow is already a huge bonus, right? Okay, so I won't belabor this point anymore. I was going to give a 3rd one, but you know what? It doesn't matter. So let's go ahead and start talking about our specific case. Hopefully, some of that resonated, and you're at least somewhat interested to know how software gets slow or why it might be slow, and to start thinking about what is the performance that's realistic to achieve. You know, are there cases like this? You know, how much software in the world is slow right now, and how fast could it be? Those sorts of things. And that's exactly what we're going to be covering. Okay. So let me go ahead and show you the grass planting stuff in The Witness. So The Witness was a video game that was done. It was the follow-up to Braid in terms of the lineage. So Jonathan Blow, who, if you don't know him, he's an absolutely amazing game designer, and he did a game called Braid, which was a big success and one of the very early, very important games in sort of the transition of indie games becoming big sellers. Lots and lots of people played it, and it was very popular. And his next game after that was called The Witness. And it was, Braid was a 2D kind of platformer. The Witness was like a full 3D, you know, if you looked at it, you might think it was a AAA game. You could walk around this huge island with tons of geometry and different things in it. You could stand up on top of cliffs and look out over the whole island, and you know, it all rendered. It looks extremely professional. It doesn't look like a small project when you play it. So it was a really big undertaking. Even though the team was quite small, programming-wise, I think there were maybe 4 total programmers on it most of the time or something like this. Not very many, but it was a very, very good-looking game. Now, one of the things that happens on these types of games is that when you have huge worlds like this and they're supposed to look really rich and detailed, is that artists need tools for putting things into the game, usually over and above what you can buy. So most of the time when we work on a video game, we also work on editors that are associated with the video game. And you can kind of think of this very analogous to something like when you build, a building. It's not uncommon to see like scaffolding, right? So scaffolding goes up around a building, and that scaffolding is something that you built that has no purpose other than to help you build the building. You will take it down after, right? And best case scenario, you use that scaffolding on some other thing. And that's exactly the same as what happens on video games. Typically, we have editors built specifically for a project. Sometimes those can then be used on subsequent projects, but they do not ship with the game most of the time. They're for internal use only. One of the tools in the editor for The Witness, in that series of things that were made for creating the world, was a thing that allowed you to distribute meshes over a surface. And the point of this is that a lot of times artists, if you imagine something like trying to put grass or rocks or things like small pebbles throughout the world, it would be incredibly tedious if you were going to actually pay artists to hand place every blade or every tuft of grass, every pebble on a beach. Really what the artist wants is just control over the visual look of these things. How clustered are they in certain areas? How distributed they are? Do they change their size or their rotation? These sorts of things. They want some parameters they can control, but they don't actually want to have to place each individual one because it's a huge waste of their time. They don't care exactly where everything is. They just care that it roughly obeys some nice distribution characteristics. So that is what the system is we're going to talk about today. And let me see if I can show you here what it looked like when you actually, let me show you this first. So here's an example of grass you can actually see. It's sort of like scattered around on the ground. There are these sort of little tufts, right? And as you move around, you can see that it just adds some nice texture to the ground. If the ground was just sort of like flat polygons there, it wouldn't look nearly as good. It wouldn't look like grass. It just looks like you're walking on like a sheet, with a pattern on it. And so the idea here is this is showing, this kind of shows depth, right? It kind of gives you this feeling of lush vegetation. And so placing those things on the ground, you can see how many there are. It'd just be extremely tedious. So this was the tool that someone had made for doing that. You can watch it run. You can see it placing those little pink like dots in there, right? Those pink placements are like grass that it's been placing. And you can see that it takes a long time. If you drag it, it has to restart, right? And it starts planting them again. I don't know if you can kind of see how that's happening, right? And so it's very, very slow. You have to wait potentially 10, 20, 30 seconds for this to update. And of course, if you're an artist trying to fine-tune the look of something, it's a long time to wait. Every time you move or change a parameter, you're waiting again for this entire process to occur. And this is a video I just recorded just for this lecture using an old build of The Witness, but on a modern machine. So this is actually probably, 30, 40% faster than it was at the time. And so it's important to remember that that's actually better than it was. It was actually slower than that in practice because the actual machines at that time were slower. And this is running on a machine that's several years more modern. So it actually isn't even representative. It was worse than that. Now, again, if you are growing up with software today and you're used to using things on the web, that probably didn't seem particularly slow. I mean, just the fact that you could drag the region in real time is something that most of the time you can't even do on web things. On web things, oftentimes you're just click and you sit there and you wait. But if you are talking about what can a computer actually do, and one thing I hope to convince you of today, that should look very, very, very slow, right? That should look like something that we can improve. And before I go into what algorithm that was using, and how it works so that you can understand it a little bit more, I'd like to take our first question pause and ask, just looking at what that was doing, because I just want to gauge your intuition, how fast do you think that should have been running? So it took maybe, and that processor, just for some reference, that was a Intel Core i7 processor from about 2 or 3 years ago. I think it's a 7700K if you want the specific one, but it's a Skylake core processor if you're the kind of person who knows processors. And it runs entirely on the CPU, so it's not running GPU accelerated, it's just a CPU algorithm. And assuming that we're not going to put it on the GPU or anything like that, because the GPU is already very taxed rendering the world and so on, my question is, stop for a second and think about how fast do you think it should run? So if it's running at about 30 seconds to plant that region of grass right now, if we were to push on it, if we were to go and try to do a good job rewriting that to be fast, how fast do you think it would actually go? Like the 30 seconds, do you think it could get down to 5 seconds? You know, or like could we double the speed? Could we get it to 15 seconds? Could we, could we quadruple the speed? Could we get it to 7-ish seconds, right? What do you think the speed would be of something like that based solely on your intuition and what you saw on the screen? So talk amongst yourselves, come up with an answer, and I've been told that the answer will then, the answer you sort of agree upon will get sent to my phone and I can see what it is. Okay, so the students averaged out when they guessed around 5 seconds. So we're going to start out with a guess of 5 seconds is what we should be able to get that down to. And of course, this was just purely ballpark estimate for them. They don't even know what the algorithm is or what's actually going on. So we just a quick read to say, what's our first intuitive guess? Okay, let me now explain the algorithm. And more specifically, first, I want to explain what the algorithm is trying to do. So if you imagine how planting works, well, we're talking about something that we want to be randomized, meaning the computer is going to randomly scatter things. And of course, anything that gets randomly scattered is just going to be using some kind of a pseudo-random number that the computer is generating to kind of place things around the world. But when we are planting things, we have certain criteria in mind that make it not as simple as just generating a bunch of random numbers. As you might imagine by the fact that that took 30 seconds, if all of it was doing was just generating a few thousand random points, you wouldn't probably expect it to take that long, or maybe you would. I don't know. Again, it depends on your intuition. But essentially what happens is that when we talk about noise, which is effectively what we're talking about here. When we talk about random things, just noise, a lot of times when we talk about random numbers, what we're actually talking about is something called white noise. And this is effectively a purely random kind of noise. It's the kind of noise that if you do it in one dimension sounds like that. White noise like on a tuner that can't get a signal, that kind of thing. White noise. And what this is it's when you just pick numbers that are designed to be as random as possible. And by random in that case, what we mean is not predictable. There's not supposed to be correlations or patterns in these numbers. If you know a few of the numbers, or even a lot of the numbers, you're not supposed to have any better idea of what the next number is going to be. It's supposed to be truly random. And the problem with patterns like this, for when we're doing things like art, is most things in the real world aren't purely random. They don't obey a white noise or a pure random distribution. They aren't simply just randomly picking things in the world and going places. If you think about what happens with something like vegetation, when something grows in a region, it takes resources. It takes water, it takes light. That means that there's always a bias for new plants that grow to grow slightly further away from that current plant than there is for it to grow right next to it. So you won't see tons of grass all right next to each other and then like a big gap and some other grass, right? Which would happen in a purely random distribution because the whole point is it's not supposed to be predictable. It shouldn't look like any kind of uniform density when you look at it because it's supposed to be purely random. So there actually is another way of looking at random numbers, a different kind of noise. And these are sometimes called like Poisson distributions or Poisson disk distributions. You can look up these if you're interested in the very technical nature of them. I'm just going to go over their properties and kind of how they work. Blue noise is a different kind of noise. It's noise where it is still based on randomness, so it's still based on picking random points, but there is a requirement that no 2 points in the distribution are so close together that they violate some minimum separation. So for example, with white noise, I can just pick random points and they go everywhere. But with blue noise, I'm saying when I pick random points, I can even think of it as doing it just directly picking random points. If the point that I would put down is too close to another point, I don't place it. So this means it still looks random and chaotic. There's not a pattern to these points, but they don't get very close together. So they're kind of more uniformly filling the space. Now, I have a diagram here, hopefully, that I can show you. And I don't actually, you know what I should do? There we go. Sorry, there's still text behind it. But if you take a look at this diagram here, hopefully what you can see is at the top on the left and right, which are really the only ones we need from this diagram, the bottom just shows the actual repulsion region of the points. But on the top, you can see a white noise pattern on the left and a blue noise pattern on the right. And now these patterns were just generated, I have to admit, I made these a long time ago because, like I said, this was a lecture, just a pickup lecture, so I had to grab things I already had. This was slides I made, or it's not slides I made, diagrams I made for some of my posts on the witness grass planting, which doesn't really cover the performance at all, but I do cover the noise stuff. And when I made these, I was not as hardcore about random numbers as I am today. So what I can say about these is, the random number generator used in these probably wasn't as good as I would want it to be today. It wasn't horrible, but it probably wasn't the very best thing. So I, take it with a grain of salt, but roughly speaking, the top diagram on the left is what happens when you just randomly place points into a plane. And so that's what the grass would look like. Now, there's many problems with these. Like I said, they're clumped together. That's not really how plants or rocks even normally are placed, right? They tend to be more uniformly distributed than that, although random. And if you look at what happens in something like that, there's another reason in games why we wouldn't want that. So besides the fact that it tends to look unnatural and weird, it also has a very negative aspect, which is when you're placing something that's supposed to cover a surface. So don't think rocks, think actual grass, not bushes, not rocks, not ferns, but actual grass. In addition to wanting it to look natural, which all those other things wanted, we also want it to kind of cover the field nicely, because we have real budgets, we have real hard constraints on how much we can render on any given frame, how much the GPU can actually render. And so if we exceed those budgets, we will be in trouble. That means we're trying to minimize the number of individual plants we place and still get a good looking coverage. If you clump a lot of them together, then even if you don't care that that looks a little unnatural, you also have the problem of you get big empty spaces, right? So you end up in a situation where you see splotchiness where you want it to feel more uniformly covered, you know? So that is the basic idea behind blue noise, and that's the kind of distribution we were trying to get. And it's pretty much what you want anytime you use an art tool. You almost never want white noise. It's very rare to want a purely random distribution. You almost always want a blue noise pattern or Poisson disk pattern. And you will notice a difference right away if you start using it for things. It's just better almost across the board. But, and here's the part that will surprise no one, it's harder to produce. So Poisson disk distributions or blue noise are usually what you want for almost anything that you're doing. It's true even for things like sampling, like when you're doing a ray tracer, you would prefer a blue noise pattern most of the time. There's all sorts of stuff that we could talk about that are why you care about what kind of noise that you use. But the most important thing to remember for this is just, again, that natural look and good even coverage are things that we really care about. So when it comes to stuff for video games, this is something that we really want to do. Okay, so how did the original version that you watched, that I played the video for on the screen, actually work? Well, let me turn that off for a second, and let me talk here about how that algorithm was working. So what happens is you probably saw there was sort of like a border region that happened, sort of like up on the, there was like a pink border, right, around the region where the grass was going to be planted. And what the original version did is it just drew random numbers, right? It just picked random numbers, and it just, you know, placed things down onto the surface, right? And when it placed these things down, it just checked. It did exactly the thing I said before. It just checked. It said, OK, whatever the distance is that's supposed to be obeyed here, just make sure there isn't anything else in that sort of radius around the point I'm placing. And if it's, you know, if there isn't, I'll just place it. So, you know, it starts placing these points and so on, right? And as it places the points, it eventually gets to some level of time when it starts, you know, when this gets kind of filled up, it starts getting to a point where everywhere that it tries to touch, right, like everywhere that it tries to place a point, is already covered. And at that point, it can stop. But it's kind of a little bit of a tough problem for an algorithm like this one, because you never really know, since you're drawing from random numbers, you never really know if you actually ran out of places to put, you know, points, or if it just seems like you did because your random numbers are not able to find the places that are still there. And to give you an example of that, let's suppose we took, like, you know, these 2 points here, right? And there is a place, you know, maybe this, maybe if we imagine one of these here, there is a place that you could put another point right there. Well, there's so little space for actually doing that at this point that having the computer randomly guess a number right in that one little place you could put it is incredibly unlikely. So there are two things that happen with the algorithm the way it was originally written in the witness. And this was written by someone else. I had nothing to do with it. This is just how it was at the time. When you do an algorithm like this, you end up with two problems. One is that the time it takes you to find a point, right, when you're guessing, it keeps going up and up and up because it keeps taking longer and longer to find where to put points, because as you get more coverage, every point you pick has a higher and higher percentage chance of falling within an occupied region. And similarly, if you take a look at the result here, you're going to have to stop sometime, and chances are you stopped when at least one of these wasn't found. So it also has another negative aspect to it, which is that it tends to leave gaps. There tend to be splotches in it that it just never found, but you totally could have put something there. So it's really not a very good way to generate blue noise. And when I was first asked to take a look at the grass planting stuff on the witness, because I wasn't really on the witness team, I just volunteered to help out occasionally on it. When they asked me if I could take a look at it, that's actually what they originally asked me to look at, was can you try to make it so the grass planting algorithm doesn't have this gap problem? And so let me walk you through that first, because I think it'll give you some insight into the algorithmic side of the blue noise generation. And then we can start talking about what the performance issues are on it. Okay. So, because right now, I haven't really talked about speed much. I sort of said, okay, it takes longer to find things, but we're really not talking about speed much at this point, right? So give me a second here to wipe off the board, because I'm going to need some more room to talk about that. There we go. And I think, let me see if I do. So I actually have some graphs here that I made when I was looking at this, which show how many times it had to try to find points as it added little pieces of grass, right? So across the bottom on this graph, you're just looking at the number of points that have been placed. So you're going through, and those are like number of number of little grass or rocks or whatever it was that you're placing, number of those you've successfully placed, and then the vertical, so the actual bar that goes up, is how many times you had to check, right? So how many times do you have to check to see if a point was occupied? So you can think of it as the bottom, going across the bottom is like one blade, whatever they are, one clump of grass, two clumps of grass, 3, 4, 5, 6, going all the way over to the right where you've got like 1,000 planted or something, right? And then the vertical is just how many points that I have to check. So, at first, I'm picking a random number. Any place I pick will probably be okay, right? So it should take, 1 or 2 max as you start. But then as you get more and more points placed, and that probability goes up and up, you end up really, really ramping up your time. And as you can see, it actually clips off the top of this graph. If I go show you the actual scaled out graph, that's what it actually looks like. So you can see how crazy superlinear that growth is. So you can see that this is an algorithm that spends most of its time at the end, right? In terms of if you assume these things are uniform cost the entire time through. Most of the cost comes at the end of the algorithm when it's desperately looking to place those final few points and it just can't seem to do it. So that's the basic idea of the original algorithm. And let me kind of explain how I went about modifying this. Now, it's important to understand when you're doing optimization work, and this in this case wasn't really optimization work, it was just modification of the algorithm to be better coverage in the first step. But whenever you're doing work like this, obviously context is important because time is limited, especially on a project like this. So when you're going in to improve something, you have to scope that improvement to be achievable. You have to say, how much is it worth my time to go do this? So we know we have to improve this algorithm, but there's a question, how much do we want to improve it? Since at this point I wasn't really thinking about optimization particularly much, I was really just thinking about how do I fix the distribution, I wasn't too concerned about generating the blue noise or the Poisson pattern. I wasn't too concerned about that up front in terms of like getting the very best generation algorithm that I possibly could. What I was more concerned about is what is a fairly straightforward thing I can do, not complicated, easy to maintain, a very simple thing anyone could drop in and mess with that will produce these patterns more reliably without those holes in them, right? So that was my goal. And I mention this only because blue noise generation is actually, I almost want to call it an active area of research. Every so often, there are new papers published about better ways to generate blue noise. And the reason for that is, like I said, it's incredibly important pretty much everywhere. It's important for sampling. It's important for art like this, generation tools. It's important in a lot of ways. And in fact, I want to say that if you look even in nature, like I said, blue noise is everywhere, and it's actually even in your eye. Your eye, which is optimized for sampling, actually has a blue noise pattern of cells in it. The receptors that see what's coming in, it's actually arranged in a blue noise pattern. This makes perfect sense because cells grow and they pack, right? And they have a distance between them, so they are kind of blue noise by nature. But also that's why when you look at things, fun fact, it's why you don't see as many artifacts as you would see if you just had a purely grid arrangement of sensors in your eye. Your eye has to do a lot less anti-aliasing than it would normally because it happens to have a blue noise pattern on the actual retina. Not my area of expertise, but that's at least something that I remember Mitchell. So Don Mitchell, one of the people who did some very, very formative work in sampling, I believe starts his famous sampling paper talking about that fact. So it's actually kind of built into us, the blue noise pattern. Okay, so what can we do first to fix that distribution? And the answer in my case was I was like, well, we don't really have to use the very latest in, Poisson disk kind of algorithms because they can get pretty expensive. And I want to say since that time, there's been at least one paper written that was not so crazy and that you probably could have considered doing in a day. But not only do I not think that was out yet, but I was aware of several Poisson disk sort of creation algorithms that make blue noise. And I knew that I could do a fairly simple one that would get us what we wanted, and it wouldn't be the most optimal in terms of the complexity, in terms of the runtime of the algorithm, but it would still be very good at keeping the cost uniform, and I thought that was probably mostly all we would really need. So let me show you what that looks like, and this is what I implemented to fix the gap and that sort of long, expensive end of the algorithm problem. Okay. So what I did was I said, well, all right, when we place a point in the world, so, we have this sort of grass region, and we're going to place a point there. We know that actually the region we're going to sample, we already know that if we wanted to look for places where we might put a point, we know right off the bat that they have to be outside this circle, right? So I put a point down, it's got to be outside there, because if it's not, then I already know that it's going to be rejected. So if I just write something that restricts random numbers generation to a disk, right, which is pretty easy to do, I can just say generate a random point in this disk and test that. Now, if we just keep doing this, that one, for example, I kind of drew this disk a little bit wrong. So we actually know that it can't be that close, so we would have to add that radius, right? So it's really more like that, right? So we know it has to be like, somewhere in this, this disk here. And I think technically these are called an annulus because it's a disk with a hole in it, right? So I know that I can just pick points outside here, and then when I pick one, I know that I can then pick points in the same way, in the annulus around that. And what I do is I just say, well, when I step through these, when I generate points, I just keep generating points around the first point until I can't anymore. So I just locally sample that one pretty densely. After I'm done, I have a new set of points, and I just go around those, sampling those densely, right? And it's just a wavefront that expands outward. So you just remember, because you're going to have to remember what points you placed anyway, because that's how you check to see if they're too close. So all you need to do is just sweep through those points, checking each of their sort of annulus regions, checking those for new places to place, and it just kind of grows outward from a point. This has the benefit of always checking that region that's just far enough away, which means that you never really have that problem of placing 2 points. You can occasionally, but much less frequently, of placing 2 points and never checking the region right inside them densely enough to find it, because you're only ever checking those regions. So if you place points like this and you just let them grow over time, you end up in a situation where your diagram, instead of looking like this one, it changes. Now I'm going to leave the blue one up there, but if you look at at what this distribution ends up doing, and let me jump ahead real quick just to show you. So here's what it looks like in red overlaid on top of the blue graph. Here's what it looks like in red to do this algorithm. You spend more time during the expansion, so you have a fairly constant test of however many you want, 30, 40, 50 or so. You're typically going to test just to make sure you fill things in. After the first few, you are still rejecting a lot of points because this algorithm is still kind of dumb. It doesn't try to not sample around where it already placed points. There are Poisson algorithms that do, and that's why I said you can do more complicated things by adding more complicated data structures. Okay, so anyway, as we go about placing these points, you can see that we spend a pretty typical amount of time throughout the entire algorithm, but it doesn't get worse, right? Because we're always sort of growing just on the outskirts of the thing. The time that we sample, we tend to always reject the same number of points, and so we really don't get into that situation where we get that explosion at the end. So we can sample the whole space fairly consistently, and we don't have to worry. And if I zoom out again to show the sort of zoomed out diagram, you can see how crazy that blue one is. I'm still drawing the red one. You just can't see it because the blue one gets so ridiculously expensive at the end that the actual number of samples taken by the red one over time are just gone. You can't even see them at that scale. Now I wanted to show you this diagram for a quick second. This is what the actual drawing of these points looks like. So on the top left, you can see the original algorithm and the blue marks. So the blue dots are where the random points it tried. The orange dots are what succeeded. And on the right, you can see neighborhood sampling, lot less blue. And again, it's not really because it wasn't still rejecting lots of blue points. It's just because at the end, the old algorithm just went nuts and had to sample thousands and thousands, tens of thousands of points all the time just to find one new one. And so it massively oversamples the space, whereas the neighborhood version does not. And on the bottom, you can see a zoom in. And what I've got there is orange. The solid orange in the center is basically where something has been planted, and the exclusion region around it, you can see, is where nothing can touch that, basically. And then the points that are placed, they would have to be able to fit the entire thing in there. So you can see that there's really no place to put on either of those diagrams. There's no place in there to put more points because the larger sort of ring would not fit if you tried to place it down. And if you look at the little blue dots, you can see all the places that were tried in both algorithms that were rejected. And there's just far fewer of them on the right. And that, right there is also kind of a speed improvement that we got for free just by trying to improve the distribution. Okay, so let me move forward here. And just say, okay, that is just the algorithmic improvement that was done, a very basic algorithmic improvement that was done to improve the distribution. It also happened to improve the speed of the algorithm because less points were tested. And now you can kind of see what we're talking about in terms of the numbers of points that had to be tested. And we haven't really talked about what that test entails, but now that you can see the number of points, that thing I showed on the screen, I think, was placing a couple hundred grass things. You could see that the cost per plant in the old one went up to tens of thousands or whatever, right? But in the new one, you could see that it kind of hovered maybe around, the 50 area, 30, 50, maybe up to 70, something like that. So if you assume you're placing 1,000 of these things and you have to sample 50 points each time, that's 50,000 tests you have to do. So I rolled that thing out because the only goal for the thing was to improve the distribution, and it did that. And hey, as a bonus, it was faster, but you could watch it right? You could still watch it kind of go out. So it was a little bit faster. Maybe it was like twice as fast. Maybe it got to like, that thing that took maybe 30 seconds. Maybe ended up taking something like 15 seconds to do the thing. Maybe it even got down to 10. It's hard to say because we didn't take timings up to this point because the goal was still not performance. But that's roughly what happened. So now we get to the second time I'm going to ask. You know that these things are sampling around 50,000 points, let's say, something like that. You know that changing the algorithm to not have this horrible long tail meant that it got quite a bit faster, down maybe to about 10 seconds. So now the question is, how fast do you think it should run? Originally you said 5 seconds, so do you think, again, before getting all the information, just intuitively, do you think that now that we're here, if we assume we're going to stick with this algorithm and not try to do a fancier algorithm, how fast should it go? Do you still think we can get a 2x improvement from the 10 seconds down to the 5 seconds that you suggested? Or do you think that we won't be able to get that many gains when we start to look at the actual performance, which is what I'll talk about next? So let me know what your guess is. Is it still 5 seconds or did it change? Okay, so the students' answers dropped dramatically. We went from 5 seconds to 50 milliseconds, something like that. They, obviously these are ballparks, so, something in the order of 50 milliseconds. Now, the interesting thing about that is if they think 50 milliseconds, then that means to me that this wave of students should make extremely performant software when they get out into the industry. So like whatever, I don't know how long it's going to take the students from this university to get to the point where they are actually making software, but I want it all to be great. So in like 10 years, when I'm using like, when I use the average piece of software, I expect it to be super performant if they think 50 milliseconds because, hey, that's like pretty interactive, right? Okay, so let's take a look at the performance situation for this, and we'll see if you stick with 50 milliseconds because, again, I'm about to give you a bunch more information about what has to happen. So, assuming we take a look at this here, we know that what we're doing is we're placing these points. And we know that we are randomly picking some points on, to see whether or not they can be used. And, I mentioned the fact, and maybe this is where the 50 milliseconds estimate comes from, I mentioned the fact that you have to check to make sure they're not too close to each other. So we know that, something like that is going to have to go on. But here's where the actual cost of the algorithm comes in. So when you look at a scene in the witness, right, and like you had that scene there, you sort of have like some kind of a underlying set of geometry, and it's pretty reasonably triangulated. And then, you've got some other things on here. Maybe there's like a wall or something on there and so on, right? And, you've got all kinds of stuff. Maybe you've got like a little, like another piece of hill coming in here that overlaps with it that kind of joins together. So you got these like gridded things. And so this is a top-down view, but when we actually go to plant grass, what we have to do is shoot a ray downward into the world, test for intersection with all this geometry, find where we actually intersected, and then we can go ahead and say, all right, now is that actually within some distance of other points that we've placed, or isn't it? And there's some other stuff that I'm glossing over here, such as there are exclusion regions, so you have to do some checks to see if you're in a region that the artist said don't place it in, or things like that. But for the most part, what we're doing is we're going to be looking at the intersection of the sort of rays through the world that intersect the geometry of the world. Now, in terms of how expensive something like that is, I can actually show you if you go to Wikipedia, so nothing particularly fancy here. If you go to the Wikipedia entry for something like how fast is it to intersect a ray, which is what this is, with a triangle, which is like what the meshes of the world would be built out of, this is an example of a typical triangle intersection routine. Not necessarily the most highly optimized one, but it was a very common one that you would have seen 2000s era for intersecting triangles with rays. And you can see that the routine is not particularly complicated if you can read C++. If you can't, I can walk you through it pretty simply. It's not a very complicated algorithm. Effectively, all it has to do is take a few cross products and dot products, and really all it's doing is it's trying to figure out whether or not you're inside the triangle, like sort of semi-barycentrically. And so what it's doing is it's saying, well, all right, I'm going to go ahead and take the ray, and I'm going to look and see whether or not, from the perspective of the direction of the ray, it falls inside the triangle from that direction, because then I would know that it must hit, right? And it produces the hit by seeing what the intersection is of that ray with like the planing equation of the triangle. It's pretty basic stuff, right? But you can see that looking at it, there's not much math in there, and the only times it ever like calls out to something you might not recognize, it's just cross product and dot product. And if you've never seen those before, they look, you know, like this kind of thing. A dot product in 3D is as simple as this. It's like 3 multiplies and 2 adds. A cross product is a little more complicated, but it basically looks like this. You know, A times B minus C times D, you know, E times F minus, it's exactly this, but 3 times, right? So it's 2 multiplies and a subtract 3 times. And that's really it. Like, there's not a lot more to it than that. So you can see that if you look at that routine, you know, you're talking about a handful of multiplies and a handful of, you know, adds effectively. So if you were to sum it up, you know, I didn't sum up that particular routine because, like I said, this was informal, so I just grabbed it. But if you look at that routine, you're not talking about a lot of math ops fundamentally for doing one triangle. You're talking about, I don't know, I mean, maybe there's 30 in there, maybe, or something. I don't know how many there are. It probably says maybe 30, maybe 40 math ops in there of the type that are floating point multiply or floating point addition. And then there's some branching in there, which looks a little ugly, especially because, you know, branches have a particular problem if they're unpredictable, which we'll talk about in a second. But if you look at that routine, you're thinking about, well, okay, you know, you're going to have between, you know, 30 and 40 math ops or something like that in there, and then you're going to have some control flow logic that has to be evaluated. And when you look at the world of the witness, I'll go ahead and pull that down so we can go back to the board here. When you look at the world of the witness, you know, you're maybe talking about one of those regions. I don't know, it might have up to 10,000 triangles that are actually in play there. Depending on how wide the region is, it could get higher. I mean, it could go up to something more like 20,000. It's hard to say. But overall, if you look at how many math ops you're doing versus how many triangles you're doing, you know, maybe you end up with some number that's something like, you know, 500,000 math ops or something like that. I don't know. And I'm purely making these numbers up, but you can see that the numbers themselves are not particularly high. However, this number here, if we assumed, you know, it was, you know, numbers of this magnitude, 500,000 ops or something, if you were going to test all of the geometry, you know, all the triangles and that sort of stuff, in a particular region that you were planting grass in, so even if you assumed you already narrowed it down just to the region you're planting grass in, you would end up doing this many ops for every time you wanted to check a point. So if we're still talking about something on the order of 10,000 points or something like that, this number does start to get quite a bit larger. You know, you can imagine that if you were actually talking about 10,000 points, you're talking about something more like adding those zeros to the back, and then you've got the zeros that we already had. And so something like 5 billion math ops, right? To test all of those triangles in the world. And so, I don't know. It's hard to say. If you were to sit down and look at this and say, how many math ops would it really take to test all these triangles? And you weren't going to try and do anything smart. You're literally just testing them all the time. You would look and you would say, well, 5 billion math ops, I guess, right? Maybe is a ballpark. Even double it to be safe. 10 billion math ops to test all these triangles or something. So that number, of course, is not really very high, is the problem. No matter how sloppy we want to get with this, 10 billion, it's just not that high. If you think nowadays about the kinds of performance that you can get out of modern CPUs, not even talking about GPUs, which are more optimized for floating point math than CPUs are, but just talking about the basic CPU that's in one of these machines, it's not uncommon to say, look, the main CPU of a desktop machine like an artist used, it might be something like 3 gigahertz. And so when you're looking at performance numbers, you can say, well, 3 gigahertz, that means that the CPU will issue something like 3 billion clocks every, second. And on every one of those clocks, it's going to be doing some work. I mean, assuming that you're not doing anything stupid, it could be doing some work. Obviously, in slow software, it isn't. But when we think about 3 gigahertz, we're thinking fundamentally about a number that's like 3 billion. And depending on what we want to say our response time is, if our response time was 1 second, we're talking about 3 billion of those units of work, right? And if we want to know for any particular frame rate, let's say we wanted to go at 30 frames a second, well, we know that we can just divide this, and that's how many clocks we would have inside one frame, right? How many times the CPU is actually going to click over. So if you imagine dividing this by 30, you would still end up with something very large, right? So we would still expect to see, even at a very interactive frame rate like 30 frames a second, 30 frames a second would be even faster than the guess that the students had of 50 milliseconds or so. And they said, it should be able to be faster than that, I think was what they said. So we're talking about 100 million of those clock cycles. Now, 100 million clock cycles doesn't tell us very much about how many math ops we could do. So for a purely back-of-the-envelope calculation, as we call it, if we want to know how many math ops we can do, we need to start multiplying this 100 million, which is already quite large, right? It's already up towards the 5 billion we might need to do the naive version of this thing in 1 second, right? To do it in a 30th of a second. We have to start multiplying this number because we know that actually the CPU can do more than this. So if you look at the way modern CPUs are designed, they are designed to be single instruction, multiple data machines. What that means is that when you issue something on a clock cycle, it's not just going to do one math op. It can do up to 8 math ops on that cycle on just one of its math units, right? So because of that, which we'll talk about that in a second as well, because of that single instruction, multiple data, a clock is not one math op. It actually starts by being multiplied by, nowadays maybe 8. AVX registers on x64, the kind of machines that we're talking about, they can do up to 8. At the time of the witness, it may have been like 4. But on the machine I showed the video of, it would be like 8. So you would expect, 800,000 math ops in 1/30th of a second. But that's just on one of the math units. The actual CPU's math units, there are 2 that can handle things like floating point multiplies. So this number would actually get multiplied by 2 again, because on every clock, the CPU can actually start 2 multiplies, because there's 2 things in it that can do those multiplies. So that's up to 1.6 billion now in a 30th of a second, right? And then finally, if we really want to go for broke, it's got multiple cores. So a typical CPU nowadays usually has at least 4 cores. So if I multiply this number by 4 now, well, I don't actually want to have to do the math, but I mean, well, all right, I will. What is it? Something like this? This is off the cuff, so all this may be wrong. But that's 6.4 billion. All of this stuff could be wrong. I'm just purely doing it off the top of my head, as I often do when I'm just wondering how slow something is and why. But already we see that if we just do some basic thinking about how fast this thing should be, even if I'm assuming ridiculous numbers, like we're testing 10,000 triangles on every point for the raycast, I already come out with a number that says that if I was using the cores of this machine and the multiply unit maximally, I actually match that number at a 30th of a second. So why was that thing that we looked at, why was it taking so long? Why was it taking 30 seconds originally, and then it only got down to maybe like 10 seconds or something after removing the really long tail part of it? So, given this, hopefully everyone understands kind of where those numbers are coming from. And in fact, you know what? I can probably show you. I think I might have grabbed some slides. Yeah. So you can actually see some things here. And so I'll kind of walk you through what this is. So one of the things that you can do, and I'll talk about this a little bit later on when we actually look at the performance stuff, is there's a great site called uops.info. This is like one of my favorite sites of all time. uops.info is a site that actually has performance timings for almost every instruction of almost every x64 CPU you might care about. And if you go look there, this, for example, is the page that you will get if you look at the performance of the multiply on x64, the floating point multiply on x64's Skylake architecture, which is what most machines were or are at the time, right? Right when the Witness shipped or so, that would have been the common machine. It's very common now. It's getting less common now. People are switching to the AMD Zens or whatever, but Skylake was the architecture that was Intel's architecture for about 5 years. Probably longer than 5 years, actually. So if you, no. Yeah, so it would be 6 years now because they're still shipping. So 5 years, I guess, like, it's 5 years. Let's just say 5 years. If you look at what these numbers tell you, you can see the latency on there, and you can see the throughput on there. You can also see some stuff like number of micro-ops and these other sorts of things that we can talk about later, and the port usage. But what you can see, the important number here is the number for throughput. And I know that I talked about latency a lot, and the problem is when we talk about whole systems and software, we care most about latency, usually. In servers and stuff, you might care more about throughput. Latency and throughput are obviously related. Latency is how long it takes you from the start of doing a particular thing to when you get the result of that thing back. Throughput is like latency, but instead of just measuring the total amount of time it takes to get something back, it asks how much does each additional thing cost after that. And the reason that this matters is because it accounts for overlap. So your throughput can be much faster than your latency, because if something, if it takes you 1 minute to do something, that's a pretty long latency. But if it takes 1 minute to do it, but every second you can start doing another one and stack up as many as you want, then it actually only takes 1 second to do every additional thing, right? So you can end up doing a throughput of a very small, it can take a very little amount of time to do more of something than it does to just do the one thing, because you can overlap the computation. CPUs nowadays are very highly overlapped. And so that's why you see like the latency of one of these instructions can be 4, 11, right, clocks. As you can see, they're up at the top. And we can talk about why they're different, why there are different ones. But the throughput is 0.5, right? 0.5 throughput means that you can do 2 of them every clock. It takes 0.5 of a clock to do it. So the latency of something, if you start a multiply, the minimum latency is 4 cycles. If you start a multiply, you won't get the multiply result back for 4 cycles. But since you can start 2 every clock, and on the next clock you can start another 2, and they all overlap, you actually end up with a throughput of 0.5 because you can always do 2 every clock. Sustained, actually. You can see that the measured loop speed was 0.53, so you actually can get very close to that in practice. You can get that many multiplies done. So anyway, you can see that we can get this information very accurately now. We aren't privy to the actual details of Intel's architecture in a lot of ways. They don't publish everything. The same is true of AMD. You're not going to get a complete schematic. You're not going to get like, here's a complete simulator of the thing and exactly how it works. But you can get pretty good performance numbers, so you can do these kinds of calculations. And what's more is we can also now talk about, well, okay, this math op stuff that I drew out on the board, it assumes that we actually have the data we need to work with. But we all, if you've done any kind of work with performance before, you know that getting the data into the chip is as important as being able to actually do math on the chip. So when we look at those numbers that say, hey, we can do 2 multiplies every clock, or those sorts of things, that assumes that we actually have the data in the chip to do it. And one of the big problems with modern chips is that the time it takes to get memory, right, from the main memory of the machine into the CPU to actually perform computations can oftentimes be the thing that actually slows us down. We can't do more multiplies if we haven't fetched the numbers we need to multiply. So you can also get numbers like these, which tell you about the throughput you could expect, like how much memory you can actually expect to get from various stages of the memory architecture of the machine. CPUs obviously have different levels of caches. L1 cache, L2 cache, L3 cache, sometimes even L4 cache, and then main memory. These are buckets of memory of increasingly larger size that are increasingly further from the CPU. So the L1 cache is the smallest piece. It's what the CPU can work with directly. It only takes about 4 cycles of latency to get something from there. And then there's the L2 cache, which takes like 12 cycles of latency to get something from there. And this is on Skylake. And then there's the L3, L4, main memory. When you get up to main memory, you're talking about potentially hundreds of cycles to get stuff from there. So you can also see that if we're able to do so many math ops, right? If we're able to do this kind of ridiculous level of math ops, we have to also take into account the fact that we may not be able to actually feed this thing enough stuff to actually run at this rate. And so we have to ask the question, well, if we're talking about something like 10,000 triangles or something like this, how much space do those actually take up? And will they fit in one of these caches? And we know from looking at that diagram that we have 32K of L1, we have 256K usually of L2, and then L3 might be up to 2 megabytes, it depends. And then usually there's main out there, which is slow, right? And so looking at these, we would start to think, well, okay, if we have 256K of L2 cache, you can see here we've got numbers on there that says, okay, what's the line size? What's the peak bandwidth? On the peak bandwidth, we may say, well, let's look at sustained bandwidth, because sustained bandwidth, it might be what we need if we're just running this thing full out. And you can see that there, you would expect to get around, 81 bytes per cycle on the L1 cache, and about, 29? So we would expect 81 bytes per cycle and 29 bytes per cycle out of L2. And the question is, well, all right, if we're only getting 29 bytes per cycle out of the L2, well, how many floating point numbers are going to fit in 29 bytes per cycle, right? I mean, call that 32 bytes per cycle or something. Figure that means we're going to take 32 and, you know, divide that by 4 or something like this, we can figure out how many floats per second we're going to be getting from one of these caches if you assume optimal, right? So I don't know, like let's say 8 times 4 is 32, right? So let's say we're getting 8 floating point numbers, right? Out of the L2 cache, we would assume that 8 floating point numbers every cycle to feed into our multiplier. Well, that's kind of not enough, probably. So, because if you think about this, if we're saying we're going to do 8 wide multiplies, we need 8 floats and 8 floats to multiply together. So it depends on, you know, we wouldn't be able to be just strictly streaming from memory. Now, the good news is when you look at it like that triangle routine, if we went back there, it's not super important, but not all the multiplies load new data. Some of them load new data, some of them don't. So we may actually be able to do this because if we can load 8 floating point numbers per cycle, let's say, we may end up getting to the point where, well, we do multiplies with some things we loaded and then we like do some adds to add them together and then we do some checks. We may luck out and find that that's plenty because a lot of our work happens with stuff we've already loaded. So we know we couldn't stream this directly. We couldn't be streaming all of the numbers in because we would hit a cache bandwidth limit probably pretty quickly because these caches are not that large, 32K and 256K. But at the end of the day, assuming we're doing a fair number of math ops with the data we load, we probably could actually, you know, we could probably actually sustain that out of L2 at least. Maybe not L1, depending on how many triangles we're talking about. Okay, so hopefully all that makes some loose sense. And now, so now what I'd like to do is just say, given all of this information that I've given you, so you've seen the triangle routine. We talked a little bit about the fact that there's caches and math ops. We know we got to do all these triangle intersections. There's stuff we can do. You know, we can structure our algorithms. There's culling. There's all these things. Before we talk about the actual performance of this routine, 2 things. One, is your performance estimate basically the same as it was, or has it moved? And the second one is, do you have any guesses as to why it was so slow compared to what this number would have suggested? Because I did the back of the envelope calculation, and it sort of seemed that like at 30 frames a second, at least the raw math kind of checks out. And there's a bunch of stuff we didn't talk about, like there's cleanup that has to happen and other things that have to go on. So it probably, you know, we're going to have to factor in a bunch of overhead. So maybe assume, you know, 2, 3, 4 times overhead, something like that. We would at least expect this thing to run in like 1 second at this point, right? So factoring that in, do you have any guesses as to where the 10 seconds comes from? Why was it so much more than our estimate? What do you think was causing that problem? And do you have any updates to your estimate now? Okay, so the students changed their estimate based on what I've said so far, back up to 500 milliseconds, which is about half a second. Still not too, it's about 10 times slower than they said before, but still massively faster than, you know, the 10 seconds that it was running at. And they said that they think the cause of the slowness in the 10-second version were things like bad, well, you know what, let me read it directly. I want to make sure I don't misquote them. So bad allocation and misses in lookups. So let me go ahead and erase the board here, and let me just say a few quick things. So I threw a bunch of stuff out there. You know, obviously, I just threw out a bunch of stuff here. I was like, SimDops this and cache that. And, you know, I don't expect everyone to know these things at the moment, right? Because people might be watching this who haven't had very much experience, and they may not know too much about these things. We're going to kind of look at these in a little more detail later, assuming that we have time. But the important part to take away from that was not so much what I did, it's that I did it. The important part of most of that was that I actually took some time to say, gosh, how much work would this thing be? And what do I expect the chip could probably do? Given the amount of time that we have, should it be this slow? That sort of thing. Now, there was a number in there that you may not want to bother with, which was the core count, because if you just want to know why something's slow, you can usually assume that it's probably single-threaded. I mean, sometimes it's not, which means it will only run on one core, which means all of those numbers would have been divided by something like 4 or potentially 8, however many cores you were multiplying it out by. But the point is simply that, even if you don't know any of the stuff I just said, if you're like, what was that voodoo that he did on the board? Sorry, I'm going to try and get this a little cleaner here. Even if you have no idea what that stuff was, hopefully you could see that actually, though, I wasn't doing anything particularly strenuous, right? You did not see me doing things like going, well, and then we take the double integral of blah and using, the Riemann hypothesis or something like this, right? Like, I wasn't doing math that you didn't already know how to do, like in grade school, right? So hopefully you can see that even if you don't know what any of those numbers were and you've never heard of uops.info and everything else, right? Hopefully you would agree that it doesn't look like something that you couldn't learn. It doesn't look like something that you're going to have to be some kind of amazing, super knowledgeable programmer to do, because all I did fundamentally was take a few numbers you can look up and multiply them together to get sort of a ballpark estimate of how many math operations this thing could probably do. Furthermore, sometimes people have already done them for you. You can oftentimes look up, this is what the number flops is. You can look up what that is. You can see how many floating point operations per second a chip is rated at doing. You don't even have to multiply, right? So that thing I did where I just kind of, was like, all right, well, maybe we've got this many cycles and maybe we've got this many math ops and so on. Really, that's just a simple, basic understanding you can gain about any chip. And once you know it, you can just kind of use that as a ballpark. Like, okay, what am I asking this thing to do? If fundamentally I'm asking it to do 10, 100, 1,000 times more operations than that number, we can expect things to take 10 seconds, a minute, whatever, because you are actually asking for that. Similarly, on those cache numbers, again, it might be confusing, but you can kind of see, like, they're rated at particular speeds, right? They're rated to go at particular speeds, and you can go, how much data is this thing? It's just counting. It's just bookkeeping, right? So I don't think it's actually particularly difficult to do what I just did. It's more the case that developers just don't do it, and they're not used to it. In class, in a university setting, since that's, what you folks are in, I would expect by now that many of the things you do in a class would stop and do that first. You would always have in your mind, what is the task we're doing? How much computing resources does this thing take of each kind? And therefore, how fast would the optimal version be? And you don't do this because you think you're going to hit optimal. You're never going to hit optimal for reasons that aren't even necessarily related to time. Even if you spent all your time working on just this one routine for like a year, you wouldn't necessarily hit optimal anyway, because optimal may not be actually possible. Hardware has all kinds of weird, intricate limitations that you only discover when you actually try to push something to the limit. And so you're never going to get the theoretical maximum of things anyway, or at least almost never. So you're not doing this because you think you'll ever hit it. You're just doing this to go, what is the order of magnitude performance I can expect out of this thing? Should this be 60 frames a second? Should it be 30 frames a second? Should it be every half second, every 1 second, every 10 seconds, every minute, every hour? And you should be able to determine that from an algorithm. If you say, here's the algorithm, we want to do it on this much data, you should be able to get that order of magnitude estimate. And I would say nobody who comes out of a university and goes into programming, or nobody who's been programming for a few years professionally should be unaware right? You should be able to do this thing. And currently, I would say the opposite's true. Most people either can't do that, they don't know how, or they don't do it. So there are probably a fair number of people who do know how to do it, but they just don't do it. That's just not what they do. So they have no idea when they're writing code usually. They're just like, I don't know. Yeah, it just does. That was how fast it ran. And if it seems too slow, I'll like speed it up a bit. But I never bothered to see how fast it should run. And it's critical to be able to do that, which is why I started with that. Okay, so again, important thing, not to be able to do what I just did right now. The important thing is to recognize its importance and go, that is something I should learn to do, and that it's not that hard at the end of the day to learn to do it if you can program. Because if you can program, you know what operations the computer has to do. If you know what operations the computer has to do, you can go learn about how those operations happen on the hardware you're talking about, and you can get the performance numbers for it, usually. Sometimes it's harder if you don't have any performance metrics, but luckily these days you usually do because someone's usually done it before you and put it up on the internet. Thank you, internet. Okay, so now we get to the question is, why is software slow? I would argue the feedback loop reason why software is slow is that people don't do that estimate I just said. So they have no idea. So the ballpark, the meta reason why software is slow is because nobody knows that it is. They've never checked to see how fast it should be, so they don't know that it's slow, so they don't fix it, right? And like I showed before, your competitors might come in and fix it for you. The iPhone may come and kindly inform all of the Windows CE vendors that their software was slow because poof, they're gone, right? But if you're wondering how you can be the software company or the programmer who is the iPhone coming along to move out the Windows CE people, as opposed to being the Windows CE people who are sitting there for a few years thinking everything's dandy until someone just wipes you off the face of the software universe, well, back of the envelope computations like that tell you what your competitors can manage because they're telling you what the optimal thing is. Now, sometimes there's algorithmic optimizations that no one may have thought of, and those can be much harder to predict because you may be able to make a dramatic improvement in the speed of something by changing the way it's done. I'm not even talking about that. That requires a certain level of creativity and finesse that is really hard to teach and is partially based on luck and inspiration. So it's hard to say everyone should learn to create brilliant new algorithms. No, it's really hard. But everyone absolutely can learn to do back-of-the-envelope computations and know that their code is extremely slow. That's not that hard. Okay, so more specifically, why is the code slow in the witness, the original code? Well, here is what the code looked like for doing one raycast. And this is a small sampling of the code. I'm just scrolling through it right now. This is only some of the code involved in testing 1 point. So just testing 1 point. This is not a looping video. This is all me just scrolling through code involved in that. Okay, so hopefully we can see from that is that there was a lot of code there. Now, my fear is that you just watched that scroll by. And by the way, that was only 10% of the code that I scrolled through. My fear is that you looked at that and didn't think that was a lot of code. Because sometimes I get the sense that people don't think that 10,000 lines of code or 20,000 lines of code is a lot of lines of code. But it's a massive number of lines of code, right? It's a huge, huge, huge number of lines of code. You could write an entire game in that number of lines of code. So that's a lot of code. Meta reason one level down. Why code is slow? Because people write way too much code. They do this in 2 ways. Number 1 is they reuse a lot of code. Reusing code is something that people have been taught to do. And there are some reasons why you may want to reuse code. But the problem with it is, when you reuse code, you usually don't think about all the stuff that code is doing that you didn't actually need to do. So in this case, that was at play. We'll see that in a second. The second one is when they write code, they tend to focus on goals ancillary to just doing the task. I don't know why this is. I'm not quite sure how we got to this place in software. But what you will see, overwhelmingly, if you look for software programming advice, if you listen to what people say in programming courses, overwhelmingly nobody talks about how to actually write code. Writing code that actually does something is almost never discussed, and not only is it never discussed, but it's never even seen to be acknowledged that knowing how to write code that actually does something is useful. Instead, you will see lecture upon presentation, upon conference devoted to things that have nothing to do with actually writing code that does anything. It'll be like, let's talk about how this class hierarchy should be organized this way because it's cleaner. You will literally find entire conferences filled with hour-long lectures by many different people where not a single one of it has anything to do with writing anything that a computer can actually do. It will all be about fictional constructs that we as programmers have piled on top of actually having the computer do things. And the problem is when people's heads are in that space, when the thing they're thinking about is an abstract notion of clean code that people concocted out of thin air that no one's ever come up with even a metric for, like there's no number, right? It's just this weird, abstract, loose thing that someone's like, oh, that code is ugly or messy, and this code is clean. When that's what they're thinking about in their head, you end up with the scroll I just saw, because you just reuse code if it's there, because you've been taught that reusing code is good. You just type in things like classes, or you use templates that are there to like do things for whatever you want to do. And at no point during that process were you going, hey, wait, what does a computer actually have to do? And why am I not just writing that? I know that sounds simple, but as far as I can tell, it's true. People just generally don't sit down and program stuff that the computer does. They tend to sit down and program things that have nothing to do with what the computer does. And the actual act of doing the thing you wanted to do is like a vague afterthought. So let's take a look at this in practice. When the old algorithm wanted to do one raycast, so remember, we are going to be raycasting tens, if not hundreds of thousands of times to test points in the world. In fact, we know that it will be like at least order 50,000, but possibly 100,000, possibly more. We're going to be doing this operation 100,000 times. Here is an example of me just stepping through some of the code. This code here, you can see in update planting, it's calling place grass. Get ground hit is for one ground hit. That called something called energy manager find by segment, which called find segment in array I, which called auto array expand, which called operator new, which called malloc base, and the two things you can't see above it, because all I did was get the function names, are actually in the NTDLL, like the Windows heap management. So they're in NTDLL. Okay? Remember, this is something that can happen for one raycast. Here's an example of actually starting to test some triangles. So you can see that we're, after get ground hit has done whatever it was doing in that last stack trace, here we're doing raycast against entities. We have raycast against entities, single entity, test ray I, test ray iterative, test ray test face. This is a stack trace for one raycast. You can see there's a KD tree involved here in the raycast, right? As well as some things like the NV library is like some kind of open source NVIDIA library that's doing those raycasts, right? So this is an example of a stack trace for one raycast. And this is a release build at this point. Okay. So let's talk a little bit about what's going on in this code. And maybe I'll turn off the actual code for a second and just talk about what the process was that happened in the old algorithm. And when I went to go optimize it, I literally sort of did what you just saw me do on the slide, which is I stepped through the code in the debugger to see what it does. Now, this is a very good thing to do. If you step through code in the debugger, not with the F10 key, not with step over, but with the F11 key, step into, that shows you every single thing that it does, even in a release build, right, in a fully optimized build. If you hit that F11 key, you will see every line of code that has to happen. Now, those back-of-the-envelope computations that I talked about, those back-of-the-envelope computations assume that every raycast that we're going to do, we basically just do the math ops that were required, right? And we're not going to do other stuff. As soon as we start to do other stuff, all of that back-of-the-envelope falls apart. So when we start to look and say, how much work are we doing to cast one ray against one ray against the batch of triangles that we need to test for this part of the world, you have to ask yourself, if our back-of-the-envelope computation was based on just the math necessary for ray versus triangle, if we start seeing that much code, ray versus triangle is not even relevant anymore. If that much code is involved in one raycast, we don't really need to ask about ray versus triangle. We've already spent the amount of time we probably had just in one of those stack traces, let alone the fact that there were multiple. It was going like in and out of those stack traces. Okay? So let's talk about what the original routine was doing. So the original routine, when it said, I want to test one of those points, what it would do is it would say, okay, step one, I want to gather entities. So the world is made up of these entities. They're basically things you place, like a tree, brick wall. They also include things like the ground. So the ground is like patches of entities that people put together. It's how level designers create levels. If you've ever used Unity or Unreal Engine or something, you know placing entities into the world is how people create game worlds. So it's going to gather entities. And what this routine did is it said, okay, usually I think it was a quad tree, which you don't need to know what that is, but maybe you do. I think it was a quad tree, but doesn't matter. The point is, it went through the world and it said, here is a line segment. And this was, again, this was code reuse at this step. There was a function that said, for a line segment, give me back an array. Well, technically it like passed in an array handle and it said, fill this array, which was like an auto array template thing in a header file somewhere. Fill this automatic growing array thing with all of the entities that overlap this segment, filtered by whether or not they have things that the grass could hit, right? So what it did was it looped through this quad tree, I think. It used to be a quad tree. I don't really remember because, again, as you'll see, none of this matters. But for figuring out why this was slow, it goes through this and it says, okay, there's all these entities in the quad tree. We narrow it down to roughly where the segment is. We start looking to see if their bounding spheres overlap this segment. For those that do, right, we remember them. So we end up with an array that maybe has, like, if this was A, B, C, D, E, F, whatever, it has like A and D. So we end up here with an array. Yeah. Don't know what that horrible symbol was. So we end up with an array that has A and D in it, right? So we have A and D in an array, and that comes back from this gather entities thing. We then say, okay, we want to loop over these entities and see if they have meshes in them that are for colliding, right? Because we're going to have to like probe those for colliding. And when we did this quad tree gather, we had some flags set. It was testing these entities' flags because they have like these fields in them to see whether or not these things, these entities, right? To see whether or not they could have had collision meshes. So we kind of know that they must have some kind of collision meshes, but they may have different kinds. So the next thing we do is we step through here and we go, okay, you know, find the meshes. So we loop through these things meshes, and for every collision mesh they have, we then call raycast on the mesh. Finally, raycast on the mesh is actually a KD tree. So there's KD trees for each of these things. And the KD tree is basically a spatial partition designed for raycasting that filters the number of triangles you test against so that you only test against ones in an order that makes it likely you'll find the hit before having to iterate through all of them. So these are the steps that happened for a raycast. So you could say this was every raycast we would do this. So every time we want to check a point, we first gather all the entities by walking the quad tree, finding out who overlaps the line segment that is the thing we're testing. We put those into an array. We loop over the array looking for meshes that are contained within the entities that are in that array. We raycast against those, which eventually is a KD tree traversal, and the KD tree traversal will return us the closest hit, and we'll merge those hits together. This is every raycast, right? Now, why was this happening, right? Why is it being done this way? Because before we talk about maybe how it should be done or what's wrong with this, we have to ask, why does this happen? And remember, this is not the worst case of development. This is actually at a game studio where people are used to performance-oriented programming. So it wasn't, you can't say that these are people who don't know that there are performance implications to things they do. They did know. But why does this happen? Well, the reason why this happens in particular, again, is code reuse. Because when somebody goes, oh, I need to make some grass planting thing for the editor, they're just like, well, the easiest way to do that would just be to call the raycast that's in the game. And of course, the raycast that's in the game, this is what it does. What else could it do? Right? So the source of a lot of slowness is exactly what you would expect. It's calling something that does what you want it to do, but not in the way that you would want it to do it. The more code we reuse, and these days code reuse is at an all-time high, usually the slower our program gets because the more ill-fit the things are for what the actual task was. On a case like the witness, it's really not much of a cardinal sin. It's a small team. They didn't have a lot of time. Until somebody complains, you might do code reuse in the editor. The player is not going to experience that. But at some point when someone complains, you got to start looking at it. And that's, of course, when I started looking at it. So this is what I saw. Okay, so probably last question for the students as we move into the final part of the lecture. Looking at what this is doing, what do you think is wrong? What are some things that you think, perhaps in order of badness, what are some things that you think are wrong about this way of doing raycasting? Okay, so I was glad to see that the students kind of guessed, or at least one of the things that they said was actually the most fundamental thing to recognize about an algorithm that looks like this. There's a lot of things we'll talk about in a second here, but the biggest one is just the fact that there's a lot of duplicated work going on here for a number of important reasons. So let's take a look at how this works. If on every raycast, we gather up all the entities that were going to be involved in this particular raycast, well, the world has 60,000, I don't even remember how many entities there were. Tens of thousands, if not 100,000 entities in this world. And they are in a tree of some kind, so there is a spatial partition that will pull them out. So we're not going to have to look at all of them. But if on every raycast we're at least considering a subset of them, we're doing a tremendous amount of work on every raycast to narrow the number of entities down. But what we know is that we're always doing all of our raycasting in a very small area of the world. There's no such thing as grass that's planted across the entire world at once, because of course the grass has to be localized and customized for every particular region. And so we never have that case. So this first part of the routine here is really bad, because it means we're doing a tremendous amount of work to gather geometry, and we have to do it every single time we raycast. So the biggest thing we can do to start to simplify things here is do this ahead of time. Do this as a prepass, right? So if we do a prepass where we say, let's just narrow the entities down to the ones we actually care about, And so we never have to do any kind of walks in a quad tree or anything like that are complex. They may have mispredicted branches in them. They may have all sorts of performance penalties lurking. Instead of that, we do a pre-pass first, and also we don't spend a lot of extra cache. We're not touching a bunch of data we don't care about. We just narrow it down to the data that we actually want. And that logic can continue downward, right? Well, we could just find the meshes. Why stop at entities? We find the meshes, we pull the meshes out. And we just do a pre-pass to say, here are the only meshes that we care about, right? And we can go one further and say, well, when we get down to a KD tree is actually kind of terrible for this kind of operation, because a KD tree is designed to handle raycasting from arbitrary directions. It's expecting the rays to just be completely uncorrelated. It's designed for general ray tracing. But we know we only ever cast rays in one direction. They just go straight down. Our rays don't go in any other direction. They just go straight down. So a KD tree, which is optimized for arbitrary ray traversal, is also wasting a ton of our time because we don't need the flexibility that it provides. So almost everything, almost the entire set of things that was actually involved in the code we saw, none of it needed to happen per ray, more or less. The final part of the KD tree thing, where it actually loops over a small chunk of faces and tests, is the only part we really needed to do per ray, and everything else could actually just be done in a pre-pass. This was obvious to me when I just started stepping through it. It was very clear that was going to be the case, because this is the kind of code that I started seeing. Just when I looked at those stack traces and I start looking and stepping through the code and saying, where are we? I see stuff like this. Now, if you look at this kind of code, it just looks like normal C++ code. And normal C++ code, or modern C++ code, whatever you want to call it, the kind of C++ code that has templates everywhere and stuff like this, is always slow, just pretty much by design. And the reason for that is that the templates don't really know much. Templates are a pretty weak programming paradigm. They can't really do very much. They're not like full meta programming. They can do things like analysis. They just do what they do. An autoarray allocates memory. It has to, because it's a growing array. And so what happens when you see code like this, where you just got autoarrays happening and people calling things, and then you got multiple layers of call stacks, that much work per array is completely impossible to make performant. If you're calling a memory allocator in the middle of a raycast, it's game over, right? That's going to be an extremely low performance raycast no matter what you do. So when you look at stuff like that, right off the bat, I'm just like, okay, this is obviously just the problem here before I even have to get into it. It's just that this is written like a regular semantic, I just wanted it to do the thing correctly program that had no concern for how fast it would run. Now, that's not entirely true, because for some reason, when I actually went and looked at the code that gathers the entities, it was multi-threaded. So somebody thought it needed to be faster, but I don't understand why, because it's a very slow thing kind of by design. So I'm not sure why threading it happened. Maybe because threading it was easy at that particular time. I'm not sure. But point being, it's clearly code that's not written for performance. It's code that's just written to do the thing and then moved aside. And so, what I want to talk about now is, well, you know what, let's not quite use that slide yet. What I want to talk about now is, how do we move from something like this to something that's appropriately built for the problem? So rather than just calling a raycast that exists in the game that's for doing other things, how do we actually build something that's going to be fast and does what we need it to do? Okay. Well, the first thing, at least for me, when I looked at that problem, is I was like, well, we really don't need raycasting per se. Because if you think about what raycasting usually implies, it's tracing a ray through the world to see what it hits. But we don't really need to trace a ray through the world to see what it hits, because we know that we're really just picking points in space in a 2D pattern and seeing like what the height of the world is underneath them, right? So if you think about this problem, a raycasting in 3D is like a whole 3D thing. That's why there's like a KD tree and entity overlap testing, all that stuff was happening. It's an arbitrary like directional problem. But we know that we are always looking at the world top down when we're doing this casting. And we know that when we ask for a particular point and we say, where is that in the world? We know that we're just talking about doing a raycast straight down. So we also just know implicit in all of our routines, the x and the y, like if you thought about the ray, the x and the y are always 0, right? The directional x and y. They're always 0. You're just going straight down. It's z1, right? Or z negative 1, right? So we know we're always casting straight down. If we know we're always casting straight down, to me that just says this should be organized like a grid. Because if I know I'm always casting straight down, I can just take the region that I'm trying to do my grass planting in, put a grid over it, and just say, look, for some density of grid that's appropriate for how big the grass planting area was, or even not, we could just say it's always 16 by 16 or something. Let's just make a series of grid cells. We'll run through all of the entities once that are involved in this. We'll take out their meshes. We'll take the triangles out of the meshes. And we'll put every triangle that overlaps a grid square into its own bucket, right? With all the other triangles that overlap that grid square. Now we have gone from a giant process that walks a quad tree, allocates array space, puts things into it, looks at those things, finds the meshes, takes the meshes, looks at KD trees, walks the KD trees, finds the triangles and tests the triangles, to something that literally in one lookup, based solely on the input x and y that we are testing, immediately gets just an array of triangles to test. So we can literally replace like the entire thousands of lines of code that were working before, every raycast, before we ever tested a triangle. Like literally thousands of lines of code. Probably, it might even get into the tens of thousands, I don't know, because you'd have to include the NT memory manager and malloc. Like all of that is on the table, right? So thousands and thousands of lines of code that had to execute before we even tested a triangle. We can replace all of that with one lookup. Back comes our pointer. We're ready to test our triangles. So we can literally eliminate almost 100% of the code that was being used in the old routine. We can erase it. It's not like we did it more efficiently. It's not like we optimized it. It's just gone. Goodbye. And so that is just moving code to the appropriate time to do it. So rather than putting it inside a loop, it's outside the loop. So if you think about this from maybe some of you have had complexity theory, right? You imagine that maybe you have something like n is the number of I'm trying to think of like the best way to write this in complexity theory. But let's say that n is like the number of raycasts that we're going to do. You know what I'm saying? And then we have whatever our like this entity traversal thing here, which is predicated on like the number of entities and the number of meshes, but we'll just call this like, you know, ent meshes or something. And this was very costly. By putting the gather step, so putting this inside the raycaster, we were effectively multiplying its cost by the number of raycasts. By moving it outside of the raycast, we are replacing that number with 1 because we only did it once. So we went from something that was not squared because it's not the number of raycasts that's going, but it was multiplicative. So we went from something that was multiplicative, which is quite poor, because as either of these numbers go up, you are sad. We replaced that with something that is linear just in the number of raycasts. And that's exactly what we wanted, right? Just from the standpoint of complexity, it's pretty easy to see why moving something out of a very high number loop. And furthermore, when we're talking about practical performance, we also care which of these numbers is high. This is a number that is going to be very high. So anything that we put in here times n is really bad, right? Any kind of thing that has to happen in here, even if it's just the constant, that multiplies, it's really bad. So not only were we putting something in that had like a high constant, we were putting something in that scales with the number of entities, that scales with the number of entities in the region, right? It goes up with the number of raycasts all of a sudden for no reason. We completely eliminate that, it's gone. That alone is enough to get us much faster than we were, but we can still do better than that because the original algorithm actually looked quite a bit like, for testing the triangle versus the ray, looked quite a bit like that general algorithm that I showed before, right? But again, what do we know about our problem? This is not a general raycast. This is a raycast where we know the ray is pointed directly downward always. So after we pull out from our grid, here are the triangles that we need to test. We can also say, well, how do we optimize that test to be as fast as possible? So let's go ahead and look at that. And I'm going to have to wipe off the board here. To have some room. The one thing I have not solved with light boards is how do you get them erased quickly? I have no idea. If somebody could make a light board someday that would, you'd push a button and somehow it would like electrostatically discharge all of the stuff on it. Like these were just like, little like particle kind of things that are stuck to it. And then you discharge it and they just fall to the floor or something. You just put a tarp under it and off you go. That will be the light board innovation. Maybe some of you there at the University of Twente, I still don't know if I'm really saying that right. Doesn't matter. My pronunciation will be bad no matter what. My accent will be bad no matter what. Maybe you've got some engineering folks there. Maybe you can design that. And then everyone can use it. Because that's like the only problem with these things is that you spend a tremendous amount of time trying to clean them. And in the middle of a lecture, you can't even really get it that clean. You just kind of have to leave it, half clean, right? So, how are we going to do this? Well, now's the part where I talk a little bit more in depth about SIMD. I'm going to avoid talking about multi-threading, even though this problem would be very multi-threadable, because I never multi-threaded the routine. It was so fast after I did this stuff that nobody cared, so I never even multi-threaded it. It was single-threaded. So we could talk about that after, but I never even bothered multi-threading it. So single-threaded, though, what's the most important thing for us to do now? Well, there's two things we want to keep in mind when we're doing a routine like this one. The first thing that we want to do is like minimize the actual ops, right? We want to make sure that we're not doing math we don't have to do. We've already done the work of making sure that we're just pulling out the triangles we might actually hit. So we've done a good job of getting rid of all of that cruft. But now we need to know, how do we actually test a block of triangles quickly? We want to don't do math we don't have to do, number one. And number two, right, is we want to take advantage of width. So we want to basically design this thing so that it is going to be really good for SIMD. So what's SIMD? Some of you probably, it seems like the answers I've been getting back, it sounds like it's like you guys know stuff, right? It sounds like I'm not talking to people who are totally unaware of the stuff that I'm talking about. So a lot of you probably already know what this is. But effectively, what happens inside a CPU, and this has been true for a long time, is that the CPU has to actually do real work. Everything we want a computer to do, the CPU has to actually do it. It's not theoretical. And so there's different parts of the process involved in how it does that work. One part of the work is figuring out what is the work. That's actually like a big part of what a CPU has to do. We call this like the front end of the CPU, and it involves things like taking an instruction and figuring out which instruction it is. Because it takes work and space, because you got to store the code, because it takes work and space to figure out what you're supposed to do, over time, chips have found, or chip makers, hardware designers, have found that it's more efficient if you can issue one instruction and do work on lots of values at the same time, because then you save a bunch of that work, right? So all the work involved in like figuring out what the instruction actually is, sending that somewhere, having someone schedule that instruction, actually execute the instruction, gather the things for the instruction, all of that stuff you have to do, whether the instruction operates on one thing or many things. So by having that entire pipeline, even into the back end, right? It's not just about the front end, but the back end as well. It has to gather operands and such, right? Having all of that operate on more than one value saves a lot of time on the chip. Because you had to decode the whole instruction anyway, you might as well, if it decodes to a multiply, you might as well get 8 multiplies instead of 1. So that's where we get the idea of single instruction, multiple data. And what single instruction, multiple data says is, well, normally we would think of having a thing inside the computer when the CPU is talking about a particular register, it's going to do like an operation. We would think about it as saying, well, okay, it's going to do something where like we have, a floating point number, and the floating point number is like 2.3, right? And then we have another floating point number, and that number is like, 7.9. And we're going to multiply these two things together, and we're going to get a result, right? And I don't want to have to multiply 2.3 and 7.9 together, so someone else can do that, but we get the result, then it comes here, right? Maybe I should have said 2 times 7. So I could have written 14, right? So inside the CPU, this would be a floating point multiply. It's multiplying one thing by another thing and getting the answer, right? And so what we've found, what chip designers say, and I don't know anything about chip architecture, so far be it from me to say that this is true, but what they say is that, well, if we could have just done more of those, right? If we could have just said, let's take a bunch, let's take 8 different numbers, right? Totally independent, these numbers. Right? And do these multiplies all together. So in one step, we get all of them. That's way more efficient. If you can find a way to do the same set of operations, but to many numbers, we can go much faster, because now we're not spending all this time decoding and preparing instructions, because where we used to have to do it 8 times to do 8 multiplies, now we can just do it once and do 8 multiplies. Now, this comes in flavors: SSE, AVX, AVX 512. Different chips have different ones of these. These are 4 wide, these are 8 wide, these are 16 wide floats. But it's all the same principle. It's just decode one instruction, apply it to many things. So we want to be able to design our architecture for this routine. Architecture is a strong word. We want to be able to design the way it works to maximize the potential for using these. Why? Because if we do it one float at a time, we are like 1/8 the speed. Not half as fast, not 4 times slower, but 8 times slower. We're 1/8 the speed if we just do it one float at a time. So being able to go wide gets us 8x speed up. If you have an AVX 512 chip, you don't really get 16x because the clocks are different. That's a long story. If AVX 512 becomes actually performant at some point, then you would get 16. On a GPU, you do often get full 16. They have full speed 16, but they're slower clock rates, blah, 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 blah. None of that matters. The point is, on a normal machine today, 8 wide is not that hard. 8 wide is a thing that many CPUs can now do. Okay. So in this case, we happen to luck out. We know we want to do things by 8, and it can be kind of challenging sometimes to do that for some routines. But in our case, we're just bulk processing triangles. That's all we're doing. When we bulk process triangles, all we have to do is make sure that we take 8 at a time. So we'll just grab 8 at a time, do the test on them all at once, and then we don't have to even really think that hard to parallelize our routine across to 8 wide, the routine. This is much harder when you deal with things that aren't quite so clearly bulk. So the first step is we're going to just say process 8 at a time. Problem solve for SIMD. Second step, what do we actually solve? So remember, we said we want to minimize the number of math ops. Well, what are the things we actually need? We only need to compute 2 things. We need to compute, did we hit the triangle, and what was the z of it? That's what we're doing, right? We're casting an array down into some kind of mesh. We're going to say, oh, we hit a triangle, and here's like how high it was, right? It's the z value. Why do we need the z value? Well, we already know the x and y, so we want to know what point it hit. We know the x and y because whatever the x and y of the array is, it can only go straight down. So we know the x and y, it's the starting. It's what we got. So the only thing we need to compute is, did we hit anything? And if we did, where, right? You could even bake this down to just one thing if you wanted to. Now, the actual routine's slightly more complicated, but only slightly, in that we also want to get an index back because we actually need to look up some properties of this triangle, such as what material it was and things like that, because these things can affect the grass planting in the full version of the algorithm. We don't really need to talk about that much, but it's not quite as simple. It's almost as simple, but not quite. So we need the index and the z, and you can think about these as already telling you this, because I could just load the index. I could pre-say that the index was some weird value like, FFFFFF, right? It's like all ones. So if you see that, it wasn't a hit, right? So we don't really need this. We can overload these by sticking bogus values in them, and if you don't get clean values out, you know that there wasn't a hit. So I really don't need this once I'm saying I'm returning these other 2 things. But I need these 2, the index and the z. So that's what we need to compute. How do we compute the index and the z value? Well, if we think about this, we're already in a prepass. We're already running through these triangles, and we're putting them into these buckets for testing based on the grid. So when I do that prepass, why not also transform the triangle into something more convenient than a triangle, right? A triangle is like 3 points. Testing for array intersection against that is actually somewhat difficult. You saw the routine before. But I know a couple things. One, I actually don't care about the z of the triangle at all. I just need to be able to reconstruct where I hit it. But for testing it, it's purely top-down, right? So if I look at this triangle, I can say, well, what if I just pre-compute the vectors that I would dot product against, and this probably gets too technical for some people out there, so I apologize. I'm not going to go, this is already very long, so I'm not going to go into detail how that works. But why don't I just pre-compute 2 basis vectors that if I dot product with them, I will get the u and v of the barycentric coordinates of this triangle, right? So I want to be able to say a u and v coordinate these are very simple things to think about. U and V coordinates just say, look, if I walk out this far along this vector and then this far along this vector here, right, I get a point in the triangle. Furthermore, if I go all the way to here, that's U equals 1. If I go all the way here, that's V equals 1, right? And anywhere in between here and here, U plus V would equal 1. Barycentric coordinates, if this was going to be an 8-hour lecture, I'd explain them. I can pre-compute exactly the transform in just a few variables, exactly the transform that transforms from an xy point, right, that we're sampling, directly to UV coordinates using just a couple multiply adds. And then I can just test to see whether or not the UVs are inside the triangle, and I'm done. Furthermore, to compute the z, all I have to do is also pre-transform to say if I know the u and v, which I know I'm going to solve for to find if I'm in there, just how do I multiply out the u and v to get me back my z? Here's what that looks like. So if you look there, M256 is just the 8 wide float. So the reason for that, you can think of that as just saying float, but we're storing 8 of these at the time. And all I'm storing there is 1, 2, 3, 4, 5, 6, 7, 8, 9 floats. The top ones, x, y, z, those are just the base vertex of the triangle, right? So you can probably still see this underneath. It's that vertex, right? The ux, uy, vx, vy are just two vectors. You could think of them as two different vectors that you dot product against to get your uv's out. And then finally, the zu, zv is just what you use to convert a uv coordinate, which we know we're going to get when we test, into the z value at that point in the triangle. That's how we pull out our z hit. That's it. All we have to do is store that. It's about 4.5 cache lines worth of data, right? 4.5 cache lines to store 8 triangles. And we can load these, test against them as 8 in one go, and we get out what we need. So let's take a look at that routine. Here's what the routine looks like. Now remember, this routine here, which is maybe a little bit hard to read if you're not used to it because it's actually written with the intrinsics. Each one of those intrinsic calls is just one operation on the CPU. So MM256 sub PS just means subtract these two things, 8 wide. So if you look there, there's only a handful of things. 15 instructions, I don't even know, 20 instructions probably. 20 instructions or so to test 8 triangles, right? So we went from that huge monstrous piece of code that was doing all these things per raycast to just on every raycast, we do one index into an array to pull out a pointer, and then we loop over that pointer running this. And that's it. Now, if we take a look at the actual assembly language, it fits on a slide. That's all we need to do. That's it, right there. And I've got notated on the side like what each step does. I just threw those in there last night so that people could read it if they wanted to at their leisure. But if you look at it, it's like trivial. There's so few things. It's like those mnemonics on the side may be foreign to you, but like V sub PS, it just means subtract two things. V mul PS means multiply two things. So it's like 2 subtracts, a few multiplies, a few adds, then we just do a few comparisons, and then we, leave. We repeat the loop, right? That's it. Now, if we actually look at what happens here, it's kind of like probably a little bit too far down the rabbit hole to talk about what this schedule's like. So I'm going to skip that. But just pulling back out a level of detail, remember all that code I scrolled through that happened on every raycast? Here is that code in the new system. It computes 2 grid indexes to see where in the grid it looks up, and then it calls that triangle routine you just saw to loop over the triangles. All that code I scrolled through, calling malloc, using autoarrays, all that stuff, it's just, it boils down to that now. Okay, so this versus this, right? And that code there was like thousands of lines of function call stuff down the rabbit hole. This one has no function calls. It just computes the grid, right? I inlined it. I think that grid call actually is a inline function normally, but I cut and pasted it in there for you so you could see it written out, all the instructions. So this had to do all sorts of stuff to get to the actual triangle testing, thousands and thousands of lines of code and function calls and everything else to get to the triangle testing. Every raycast, this has to do one simple calculation and a lookup. Okay, so here's the actual routine running. And what you can see here is that you can just actually drag it around. Your guess of 500 milliseconds is actually not bad. It's extremely simple to move now. You can almost get it. It's not quite 30 frames a second, but then again, the editor is kind of slow at updating the meshes. So actually, the bottleneck here is not that triangle stuff anymore. If that makes sense, I can run that for you one more time so you can see the final speed. Or maybe I can't. I don't really know. I've never tried to do a slide presentation this way, so I don't actually know. It looks like it can't wrap around or something. So again, going from something that takes 10 seconds more really on that machine to something that you can just kind of move around and it plants pretty much instantly as far as you're concerned. And again, once we had this, we could have gone way faster, right? I could have then multi-threaded this. I could have cleaned up the gather code, because the gather code, which is taking a ton of the time, is actually just the same as the old gather. I just only ran it the one time, and then I processed the triangles, so that really didn't get any faster. But you can see that the difference is staggering. So rather than something that you sit there and watch and you wait, it's actually something that's just instant. So now, I'd be happy to take questions. We can obviously go into more detail on any of this, but that was already a ton of information. But I just want to close the non-Q&A part now by just saying, in general, software on today's hardware can pretty much always be very fast. The hardware is kind of amazing, and even the networks are amazing. So there really isn't ever any reason anymore for things to be slow. The reason they're slow is because we don't spend time making them fast. Sometimes there's a very good reason for that. I feel like on the case of the witness, there was a very good reason that routine was slow, and that's just because the person who was making it the first time was just trying to get it done so they get back to what they were doing, and it was for internal use, right? The same people who made that routine probably spent a lot more time optimizing stuff that was actually going to run in the game because they knew that had to be fast. In general, though, that step that we then took, which is somebody came after the fact because it was too slow, figured out why it was slow, wrote a faster version, and put it in place so that people could actually get good results, fast results from the software they were using. That part pretty much never happens nowadays. It seems to me that most of the time, people only do the first part, and nobody comes along to do the second part. There may have been a good reason why something was slow the first time you did it. One of the reasons is you had to do it to the side like that, where you didn't have time to actually go focus on it. Another reason might be that you're exploring possibilities. You don't know that this is something you're actually going to ship or use, so you just hack something together to see whether it does the things you want it to do. And that's all fine. What's not fine is that increasingly we are never taking that second step. No one else on the team or the person who originally wrote it is never going back and going, we need to make this actually be good now because people are actually using it. Instead, they're just letting everyone waste all their time. They're burning up, I don't even want to know how much heat is being generated right now because nobody does these extra steps. So they're just wasting tons of data center time, tons of money. They're wasting so many user hours on these things. And at some point, I feel like we got to start focusing on performance. And to me, it seems like the incentives are there. Everything that I've seen from computer history suggests that if you can identify an area where people are shipping slow software that's unresponsive and annoying to use, which is almost all software currently in existence, if you come out with something that is reliable and fast, that has that low latency, really nice interactivity, people switch. They switch. It's an avenue of attack that competitors can exploit. So I think as we see more and more competition start to build up, because remember, when you start something like the internet or whatever, there's an initial rush of people just doing things because no one's ever been able to do them before, right? No one was ever able to make, Twitter or something because the world wasn't all connected by a network. So yeah, the first things of those, there's not much competition. Most of them are lousy, right? Most of them are slow. Most of them are buggy, whatever. But they'll still succeed. As that ratchet tightens, and there's not so much low-hanging fruit anymore, the benefits for competition on performance start to go up. Because what else are you going to do? You can't come along and say, check out this new messaging service that I made. It's exactly the same as the old one and just as slow. Who cares, right? You need competitive advantages. And I think what we've seen is that when someone enters a market and demonstrates an awesome version of something that used to be crappy, people notice. It's not actually the case that people don't care. They do. It's just right now they don't have any options. So of course they use something like Twitter with all of its problems and it being super slow and unreliable and all these other things. Because what else are they going to use? But I don't think that means performance doesn't matter. I think it means performance doesn't matter when there isn't anyone else doing performance. I think once you have a competitor enter with performance, there's a lot of evidence that suggests that that is a powerful market position. So I would say I don't think this is just for show. I don't think it's just for fun. I don't think it's just for being honorable. I don't think it's just about doing a good job. I think there actually are tangible reasons why, as software developers, people should start to care, for real, about how fast their code runs. But we'll see. Maybe I'm wrong about that. But it certainly seems like that would be true. I'm happy to take questions now, if people are still sticking around. I will check the Discord, and I'll also pop in on the Twitch chat. But thanks for watching. Okay, so I've got some questions from folks, both students and the Twitch chat. And I'll try to answer these as best I can. So the first question was actually asked during the lecture and was queued up. And that was asking effectively, what about fractals? So going all the way back to the original when we're talking about blue noise patterns for distributing plants throughout the world or grass or rocks, how about fractals? Do we consider using fractals? Are they good? Is there a problem with fractals? Like, et cetera, et cetera. And what I would say about that is twofold. One, no, nobody really considered using fractals for this as far as I know. I could be wrong about that, but I don't think so. Two is, yes, I do think there's a reason why you want blue noise instead of fractals. Fractals are like self-similar, and they tend to have a certain regularity about them. You can do things to fractals to make them appear more random, but they generally don't look like those kinds of distributions that you see in forests. Like, they don't look like a blue noise distribution. If there is a fractal that produces something close to a blue noise distribution, that might be a very interesting idea. I just haven't seen that fractal. So when you're talking about using fractals to simulate things in nature, at least all of the fractals I've seen, they're never talking about this, right? This particular thing where we want things randomly placed, but so that they have a specific factor there of not encroaching on each other's sort of space. I haven't seen fractals that reproduce something of the quality of blue noise. If you know of one, I would love to hear about it. So please do send me a note, because I don't follow fractals particularly closely, and this is not my job every day, right? Like, I don't go to work and think about how to do nature placement algorithms. This was just me optimizing a routine that was used in the witness editor. So I could easily have missed some of the state of the art on fractals since it's not something I normally do. Okay, so another question was, how did the original version know when to terminate? So that original version that randomly picked points, how did it know when to terminate? And this is one of the problems with that way of doing blue noise is you don't know how to terminate. So it's usually ad hoc. Usually it's like, if I test this many points and I can't find anything, I'll stop. That's sort of similar to the way you would do it in the other algorithm, only it's very unreliable because you're trying to guess something totally random. Whereas the other one, that's a wavefront kind of approach that was the one I replaced it with, you can tune that number to a very specific number that will always work. Whereas the one that's about guessing how many times you should stop on the last iteration is kind of arbitrary and hard to test. So it's not great. You can do that. The other thing you can do is you can say, well, I'm only going to place X number of these things. And the user places that number in. And at that point, the user is kind of responsible for finding the right number, which is not great. You usually don't want that. But again, it doesn't have a very good termination criteria, whereas the other one does, which is nice. So now moving to some other ones. 2 questions. So the first one is, do I think IDEs cause some of the bad habits I was talking about? And 2 things. One, I would say, I don't know that this is necessarily, I wouldn't necessarily use the term bad habits. I would use the term lack of good habits. And I know that's a pretty odd distinction to make, but reusing code or cutting and pasting things or calling a library, they're not bad habits per se, because it's not like you don't want to reuse things sometimes, right? I mean, even take, for example, something like a math library. It would be crazy if you hand wrote in SIMD all of your routines all the time, because most routines don't need to be that fast. So you're probably going to want a dot product and a cross product, and you're probably going to use them. I certainly do, and they don't really cause much of a problem. So it's not so much bad habits as it is lack of the habit of actually looking at the things that you do and go, is this slower than it should be? And when it is, rectifying it. It's more like getting a good habit, and it's not about bad habits, because most of the habits that cause this are not in and of themselves bad. It's the fact that you're never checking them, right? Using a library isn't bad if the performance you get out of the library is roughly in line with what the machine is capable of. Sometimes a library will do, like, let's say you have a library for loading and decompressing a PNG. Well, that's like a one-shot thing. I just say decompress this PNG. It might be able to be as fast as it can possibly be, right? It doesn't need to really be specialized for what I'm doing. I just want this RGB image out. It's roughly right. There's not much modification I really make to it. That library may just be peak performance. Someone may have already optimized it and it's really good, right? So it's not a bad habit to reuse code. It's a lack of a good habit. It's a lack of saying when you reuse code or when you write code to do something, are you actually checking to see whether it's like 10, 100, 1,000 times slower sometimes than it should be. That check is the good habit you need. So to the extent that there's a bad habit, the bad habit is just not checking. But I would call that lack of a good habit. As for whether I think IDEs are implicated there, not really. An IDE is fine. There's nothing particular about an IDE that discourages you from doing back-of-the-envelope calculations. And to be honest, Godbolt, for example, if you've ever seen Godbolt, it's not an IDE, but it's sort of like an IDE, right? It's actually very good for learning about performance. Integrating things in can reduce the amount of time it takes you to ask questions about the performance of your code. So to the extent that IDEs are a problem, it would only be that they don't have as many features as you would like for performance. But that's not inherent in the fact that it's an IDE. So I don't think IDEs are really implicated at all here, other than to say there's things they could be doing to help that they're not doing. And Godbolt is a good example. Godbolt is an example of having a integrated system that really helps with performance investigation. So, I think there's things we can do with IDEs that would help. Far from being a hindrance, I think they could actually be a help. Just right now, they're not really, except for Godbolt. Another question. Why SIMD first instead of multi-threading? So the answer to that question, I can give two separate answers. The first answer is that you pretty much always do SIMD first because you have to do the SIMD before you do the multi-threading anyway, because the multi-threading is just going to run the SIMD code, right? So I usually SIMDI something first because you're going to want to run, if you're doing performance, you're going to want to do both, and you're going to want to SIMD optimize the thing and figure out what actually has to happen, because multi-threading something assumes you've already figured out what the algorithm is, and since the algorithm is going to be dependent on the SIMD, at least the base part, the inner loop kind of has to be known before I start thinking about how I'm going to multi-thread it. So usually the answer is that, but in this particular case, it's pretty simple. The core count at that time was pretty low, 2 or 4. It wasn't 16 or 32, right? So you know you can get an 8x speed win, or 4x at least, but an 8x speed win for going wide. You ain't going to get an 8x speed win for multi-threading. So kind of right off the bat, you know you get more from SIMD than multi-threading. Nowadays, if everyone at the team had a Threadripper on their desk and it's 64 wide, well, that's not true anymore. 64 thread, or 64 core, 128 thread. Sure, that number is a lot more compelling now. So you're going to be thinking heavily about the multi-threading as well. But even so, I'd probably do SIMD first because I have to know how that core throughput works before I can design the algorithm that actually does the work distribution, right? So just something to think about there. Now, finally, this one's a little bit more in-depth. I'll go check for more questions in a second here, so this doesn't have to be the end, but the last question that I saw when I was grabbing stuff off camera there is how do you check for the UV in a triangle test case? They were just curious about that. So let me just say really quickly how that works. It's not that hard. So if you think about barycentric coordinates, let me just kind of show, since it was asked, and we're now just in overtime, so we can do whatever we want. We don't have to be careful, or we don't have to be. We can be the opposite of what we're talking about. We can be inefficient and sprawling, right? So in terms of what we're talking about with barycentric coordinates, I just kind of threw that word out, but I didn't really talk about it inside the meat of this presentation. But I can kind of talk about it now. Barycentric coordinates are actually very simple to understand. They just take a little while to get used to using because they're not probably, if you haven't, my recollection from my programming career anywhere is when you first start thinking about I'll call them multi-way blends, n-way blending. I usually in my head, I think n-way blending. When you first start thinking about these things, it's very unintuitive, and then it becomes intuitive later. Now, part of that was because it was not explained well back in my day. Nowadays, like, you've got explanations out there. I mean, I've put explanations out there that I think are much clearer, and so it's easier to kind of learn than it was. So it's unintuitive at first. If someone explains it well, you could probably get it faster, but it does take a little while of working with to really understand what's going on. But it's a pretty simple concept at its base. If you think about 3D graphics at all, or even just 2D graphics, even not even think about graphics, just math, we're very used to the concept of basis vectors, whether anyone's ever even mentioned the word basis vector to us or not. And the reason for that is we're always sitting there when we're doing math, even in grade school, even when we're little, we're always talking about things like x and y, right? And when we talk about a point, you know, it may seem second nature to you now, but there was no reason why you had to say that the way we specify where a point is that you walk out along the x-axis a certain distance, and then you walk up to the, along the y-axis a certain distance, and you arrive at the point, hence the xy notation for 2D points. Because that's what we're doing, right? We're saying go this far along x, go that far along y. X and y are the basis vectors for the standard Cartesian plane kind of stuff that you see in math class. And you may never have thought about it that way, but when they first taught it to you, that's what they taught you to do, right? Go out, whatever the x-coordinate is, go out this far. Whatever the y-coordinate is, go out that far, plot the point. So you always thought of it as basis vectors. They're vectors you go along to get places. And at no time are people using like polar coordinates and stuff like this usually. Nobody's talking about, well, go start pointing in this direction and lift that far up and then go that far, right? We all are now just mostly talking, whenever we talk about graphics, we talk about 2 basis vectors x and y, 3 basis vectors x, y, z, and how far you go along them. So it's what you intuitively do. You don't intuitively think usually about like polar coordinates or any other. There's so many other coordinate systems we could use. This is the one we use. So the idea behind barycentric coordinates, especially for triangles, is that we're just going to reproduce that same thing but just for the triangle. So instead of thinking of this as an arbitrary space that we're just using to describe points, what we're going to do is take a very specific 2 vectors, u and v, which are the same as x and y. You could call them x and y if you wanted, but we usually reserve x and y for talking about like the world, right? The main space. But we're going to take 2 vectors, u and v, and we're just going to say that our triangle is this beautiful right triangle, right? And the u, this point is 1, that is 1, right, along the axis. So our triangle literally is this perfect, nice right triangle centered at the origin, well, not centered, based at the origin, right angle at the origin. Its v coordinate at the highest point is 1. So this point right here would be 0, 1, right? 0u, 1v. This point, the other point on the triangle is 1, 0, right? 1u, 1v. Barycentric coordinates just says it would be really great if we could always just talk about it this way. Because how simple would all of our math be? And so, for example, in this case, I want to know if a point is inside the triangle. Well, first of all, I can trivially test to make sure that both values are greater or equal to 0, right? So I can say if u is greater than or equal to 0 and v is greater than or equal to 0, I cut out all of the space, right, outside of the triangle that way. And then the only thing I have to do is get rid of the triangle, get rid of this part, right? I've cut out everything on this side, I've cut out everything on that side just with 2 tests. And all I need to do is find out if it's past there. That turns out to be extremely easy as well. Why? Because we know that the line between these two, right, smoothly goes from 0, 1 to 1, 0. So as I move between them, right, and what would this be right here? That would be 0.5, 0.5, right? It's a smooth line on a right triangle, perfect 45 degrees. I know that everywhere on here, my u plus my v is going to be equal to 1, right? Because I know that I went all the way to 1 to get here, and if I start walking backwards, I've got to go all the way to 1 to get here, so I trade off my 2 values, right, as I go between them. And any point that I find on here, it's always going to have u plus v equal to 1. So if I just demand that it's less than or equal to 1, right, then this is sufficient for saying I'm inside the triangle. 3 tests. That's it. So it's really, really convenient if you knew you were in this form. The problem is you're not in that form, pretty much ever, right? All the time you're given things in the actual world, the actual triangles, they're not these perfect triangles set up at the origin in exactly this form. But, like I said, we have preprocessing. So what I did for this routine is I just said, look, let me just pre-compute the transform that maps each individual triangle in the world, right? I've got some arbitrary triangle, you know? Let's just compute the thing that maps it so that, you know, the base is here, this is here, and this is here. And I can always do that, right? I can always come up with a spatial warp that puts the world of the actual triangle into this perfect right triangle. It's just a straight affine transform, right? And that's all my routine was doing. It affine transforms not the triangle, because we already know that, we took the triangle, we have the affine map. It just takes the point. So if the point that we're testing is here, it just maps the point with the affine transform, right? And it gets like there. And so now we know the UV coordinates. They're just whatever the result of the transform is. So thinking about it this way is kind of handy. This is the kind of thing you do when you are heavy on prepass. These triangles aren't moving, right? Because we've fixed them all. We're going to do tons of raycasts against the same geometry. They may have been moving in the real world, but we're fixing them right now because we're taking a snapshot in time and planting the grass on it, right? So we're gathering all the triangles. We can compute these. But we're doing a prepass. We just compute the transform. Even though that's kind of expensive, we compute the transform once, and then on every raycast, it's just a simple mapping. And the mapping, it's a regular transform. It's like a matrix, it's a 2D matrix transform, right? So it's literally just, a subtract to base this vertex here, and then 2 dot products to warp the space into a right triangle. And then this is the exact question you asked, is what's the check? It's that check. Now, if you want to see what that looks like, I can grab that. Well, or maybe I can't. Hold on a second. Yeah. So here is that actual routine. And what you can see, if I kind of try and point directly to it, do you see these comps here? There's like a V comp. There's a couple of V comps, 1, 2, 3, 4, right? Those 4 V comps are what's doing the check. 3 of them are these, although they're phrased differently. I like to do things in SIMD with the same kind of check, because if you want to port to multiple platforms, you want to just be able to write the code for the mnemonic for that check and not have to support them all. So I believe the way I check it, in fact, I think I wrote it on there how it was checked, right? It's less than, they're all less than or equal to, yeah. So we flip these, right, and we do like 0 less than or equal to U, or like 0 less than or equal to V or whatever, right? So you might flip them around to get them all going the same way, but 3 of the tests are this. And then there's one more test. You may be like, what's that test for? That test is there because, remember, we're planting the grass by shooting a ray downward. We want the closest point that we hit. So the 4th test is, are you closer than the closest point we've already found? So we do 4 tests. 3 are we inside the triangle, and 1 is, are you closer than the previously closest hit? And you can see those in the assembly. It's just 4 comparison operators. Now, we didn't really talk about this, but in SIMD, one of the other things you'll notice about this routine, actually, if I go back, it's branchless. There's no if statements in this routine. So how does that work? Well, the answer is, in SIMD, if I know that I'm going to batch process a bunch of triangles, and furthermore, in this case, I not only know that I'm about to batch process a bunch of triangles, I know I can't early out. I got to test them all, because there always could be, I've already culled down to a small set that's right around me, and I have no idea what order they go in, right? I'm not going to jump around. I'm just going to blow right through them as fast as possible to avoid doing any kind of weird, unpredictable patterns or anything like that. So I'm just going to blow through like 10, 20, 30 triangles as fast as I can. Maybe a few more, I don't know, 100, 200, whatever the optimal size ends up being. You'd shrink your grid, right, till you got to a good size. But if you look here, it doesn't do any branches. So how does it get the answer? And what happens is you just do it 8 wide. So you test the ray against 8 triangles at a time, and you just leave the closest result in a sort of state register. You've got one register that just sits there, and it keeps the closest hits. 8 closest hits. It's the 8 lanes of the computation. You still just have the best hit in the 8 ways of the thing, right? So we're actually not testing for the closest hit. We're testing for 8 closest hits in what amount to 8 separate test phases, because we're getting buckets of 8 in. we're testing them, and we don't want to have to collapse. We want to just leave it that way. So we just keep overwriting using masking, test and mask, right? We just keep using test and mask to gather in the 8 lanes the 8 best hits for those one for each lane. And then only when we're done testing all the triangles do we then collapse that. So we have a little thing, it's not on this routine. There's a little thing at the end of this routine that just looks at which is the best one of the 8 and picks that one. So that's how that part of the routine works. And I know that's a little bit hand-wavy, but you can imagine, I can make it a little more concrete for you if that's confusing. Let's suppose I have 2 floating point values, right? So I've got, I've got a equals 5.3 and B equals 7.9. So just in a regular programming language. I want to know which of these numbers is less, right? So if I were to write it out in like if form, so like I was going to actually do a predicate, I would say something like, if A is less than B, then, whatever I want the result to be, result equals A, else result equals B. This is how you would normally, do a test. So this doesn't work if you're doing things 8 at a time, because this answer, there's 8 answers. If I have 8 floating point numbers I compare to 8 other floating point numbers, there's 8 answers to whether it was less or not. So the way these sorts of things work is when you ask for the test, it actually just produces a mask. So when you do that test, you get a mask back with 1s everywhere the test passed and 0s everywhere it didn't. So this will just be like all 1s, this will be all 0s. Not in floating point, in binary. These are the bits, right? So then what you can do is you can change anything that you were writing this way. So instead of ever writing A less than B, right? Instead of writing that way, you just write the result, and we assume we've got this mask, right? The result equals the mask, remember it's 1s where it was true, right? So we want A anywhere it was true. So the mask ANDed with A produces only A's values where the mask was 1. We can OR that with not the mask and B. That produces B's values only where the mask was false, where it was 0s. And this, branchlessly, right? There's no if in here. Just using binary combines the values properly. And this even works with just one value, right? If we imagined instead we've computed a mask of all 1s, if A was less than B, this would work. But so everything looks like this. And that's why if you look at the routine, you see all those and OR, right? I assume are in there. vcomp, vblend. Oh, so there's no OR because it uses a vblend. So this construction here is actually a built-in operator, a built-in opcode. On x64, it's called blendv. And it literally does this for you in one instruction. So it's usually faster than doing it manually, depending on what you're doing. Okay. Hopefully that explains how that works. All right. I think we've handled everything. Sorry, but I forgot that the slide was up there. It's hard because I can't see very easily. This is the first time I've done this, so I don't actually have a good way. I need to figure out some way to place something I can actually see, so I can see what's up there for slides, because I don't normally do that. Normally I just do lightboard stuff on the lightboard. I don't have slides, so I don't have to worry about it. But it would be nice if I could see it. The problem is if you put something in front of the lightboard, it'll reflect. So you kind of have to figure out a way to put it somewhere where it won't reflect. It's dicey. All right, anyway, that's it for questions. So thanks everyone for joining me. And yeah, hopefully there was at least a little bit of a glimpse into like why software tends to be slow and generally speaking, how you can go about combating that. It's really not that hard. It does take learning to learn how to optimize stuff, but it actually doesn't take that much learning to know how to tell it needs to be optimized. And so that's actually a good thing to learn, even if you don't know how to optimize yet, because you can always ask somebody, right? You can always try to grab someone more senior or something and say, look, this thing's really slow. What can we do about this, right? Like I know this could go a lot faster, so like what's going on here or whatever. It's just knowing is a huge part of it, and the techniques and learning how to optimize will come the more practice that you have. So that's it. Thanks for joining me. And for those of you who are regular viewers on the Handmade Hero channel, I'll see you this Saturday. For those of you who aren't, thanks for stopping by. Take it easy, everybody. That's the end of the lecture. I hope you enjoyed it, and there was some interesting stuff in there for you. Again, the Kickstarter is now live, so please check it out. The link's in the description below. And if you have any ideas of stuff that you'd like to see on this channel while we're doing the Kickstarter promotion, please don't hesitate to hit me up on Twitter. It's at CMURATORI, at CMuratori on Twitter, and I will put it in the rotation. Thanks, everyone, for watching, and I'll see you on the next video.